Neredeyim ben? Hocam günaydın. Selahattin hocam.
Günaydın. Günaydın abi.
Hocam nasılsınız?
Teşekkür ederim. Her şey yolunda görüyorum. Gayet güzel. Tebrik ederim.
Sağ olun. Biz de şimdiden teşekkür ederiz. Hocam birkaç dakika sonra siz başlayabilirsiniz. Bundan sonra siz.
35 dedi bana Ceyhan ama bekleyeyim biraz daha.
Yo 35 şu an zaten bir dakika sonra 35 olacak hocam.
Evet, 35'te başlıyorum. Tamam.
Evet, evet.
Tamam, peki.
Tamam hocam, sağ olun. Teşekkürler.
Teşekkür ederim. Good morning. Welcome to 10th Atmospheric Science Symposium. And today morning session title is Air Pollution Modeling. I'm the session chair. Let me introduce first. My name is Selahattin İncecik. Earlier from ITU, Istanbul Technical University, now IUAPA, International Union of Air Pollution and Prevention and Environment Association. This morning we have 7 papers. We have each paper will be presented in 15 minutes. I will use a signal when there are 5 minutes and 1 minute left to finish 11:20. Okay, maybe we can start. The first paper is characterizing inhalable major elemental components of PM2.5 in Istanbul and their impact on pathogens, a case study during COVID-19, consecutive lockdown and unlockdown days. I think that this paper will be presented by Aslı Baysal.
Good morning, everyone. I'm Aslı Baysal, and today I present 2 presentations about PM2.5 particulate matters and their toxicological impact. And the first of all is about a case study during the COVID pandemic and their different application of the lockdown. Firstly, as we know that atmospheric particulates include both biological and chemical components, and chemical components include metals, organics, and ions, and also biological components are pollens, bacteria, viruses, and fungi. So all of together make atmospheric particulates, and they inherit these all components penetrate the deep lung and can cause different diseases such as cancer, allergy, pulmonary or respiratory impact or health. And there's a lot of in vitro, in vivo, and epidemiological studies about their causes of the disease. And also, when we do particulate method penetrate the lung fluids, there is different behavior. Since lung or human body has different media, and this media includes different kind of dissolution properties. So metals and organics and ions behave different bioaccessibility in this media. For example, in lung fluids or in lung, there is different condition. For example, in normal health condition is a gamble or inflammatory conditions, and phagosomal or alveolar macrophage fluids can be dominated. So elements or organisms different behavior show. I said that lung has different compartments and different conditions. So gamble solution is a scientific solution and simulates the neutral lung fluid to simulate the extracellular fluid composition in the skeletal muscle, and the simulated the intestinal fluid dip within the lung and mimics the normal health condition. Contrary, alveolar macrophage and phagosomal fluid is acidic pH and also shows the inflammatory conditions. So it is important to their dissolubility of the metals is important on the behavior of the elements. And in this study, it's a case study, and our aim is to total and inhalable major elemental components in 2 PM2.5 filters, and then their impact on the pathogens. We use the pathogens model system since pathogen can cause different bacterial sepsis or other respiratory infections. So we try to understand how these different environmental or anthropogenic conditions impact the bacterial responses. So after collected the samples with 2 different environmental conditions, we also extracted the 2 types of simulated biological lung fluids to mimic the inhalable conditions, and then the sampling place is near the industrial places and also highway and airport properties in this area. So this is maybe not important on the PM2.5 mass concentration, but it can be impact on the major elemental components. We actually use the major components because bacteria mainly use the major elemental components since their major living properties related to major ions. Yes. We also calculate or measure the major elemental component in two different simulated biological fluids. And as you see in the table, in normal lung fluid, sodium, potassium, and iron is higher than the in weekends than the weekdays. And also it is important, and also in ALF conditions, which is inflammatory conditions, contrary to the Gamble solution, sodium, magnesium, potassium, and is higher levels than weekdays, and it is maybe important in the bacterial responses. This different behavior can be obtained the pH of the sample media, and also their constituents different, so molecular dissolution can be impacted on this element's dissolution. And to understand their impact on the bacterial responses, we use the model system through the Streptococcus and Pseudomonas aerogenes. And as you see that, in Bacillus, as we see that in the picture, Streptococcus and Bacillus under inflammatory conditions were not affected from the lockdown or unlockdown deaths, because their controls and these medium are not different to each other. On the other hand, intestinal fluid within the lung conditions increase the bacterial viability in weekends compared to the weekdays and controls. The results indicate that the inflammatory condition repress the anthropogenic impact on the tested bacteria. Contrary, intestinal fluid within the lung conditions influence from the anthropogenic source and decline the viabilities. Viability is important because the pathogen or inflammatory respiratory illnesses can cause from the higher viabilities of the pathogen. And another important bacterial behavior is biofilm formation. Biofilm formation is the colonized form of the bacteria or pathogens. Since under harsh conditions, bacteria can try to survive and make a biofilm, and also many antibiotic resistance bacteria form the biofilm formation. So it's important for the toxicological responses. As you see the figures, similar responses were obtained under Gamble solutions, and which is normal conditions. And biofilm production increased at lockdown weekends compared to the unlockdown weekends. But both biofilm responses were lower when the presence of the outdoor PM2.5 rather than the control group. These results can be originated the higher major elemental composition in the weekends under normal health condition of the lungs. On the other hand, under inflammatory conditions, biofilm formation behavior of Streptococcus and Bacillus was varied and unsignificant and wide amount of the Bacillus biofilms formed in weekdays. However, restricted and lower amount of the biofilms produced at weekends compared to the control group.
1 minute left, please.
Biofilms were similarly varied and higher at weekends. All these results also impact. These results can be caused by the metabolic activities of this bacteria, and we also examined the metabolic activity of these bacteria. So these figures are related about the mechanism of the bacterial responses. Main metabolism is living systems can be occurred by protein metabolism or antioxidant systems. So these results is about their protein production and antioxidant mechanism. And the results indicate that both protein and antioxidant behavior have a role on the bacteria viability under inflammatory conditions, whereas under normal health condition, only protein metabolism can be impacted on the viability of this bacteria pathogen. This is important because antibiotic resistance solvation can be done by this metabolism activities, and all these results show that outdoor PM2.5 make a substantial contribution on the specific microorganism and specific condition of the lung. So all these results indicate that the importance of the airborne characteristics on the bacterial responses and human health. Thank you. Maybe that's any questions? Okay.
I think Professor Salatin has lost his connection. Is he here? Oh, he's gone. Sorry for the connection problems.
Okay. If you have any questions, I can explain.
I think the second presentation is yours
Yes.
also, so we may continue to that.
Okay. Now another presentation is about the monthly monitoring of the PM2.5 samples. It's important since the seasonal temporal pattern is important again on the health issues. Yes, and now we presented the investigation of the outdoor PM2.5 oxidative characteristics and impact on the activity and biofilm production of the bacteria. We mainly focused on the bacterial responses because bacterial response can cause some respiratory, critical respiratory inflammation and can cause higher mortality and morbidity for the human. So this current study investigates the 1 year monitoring of the outdoor PM2.5 in Istanbul, Turkey, and characterize their oxidative characteristics and examine their monthly impact on the bacterial activity and biofilm production using the lung conditions again. So first we collected the samples by monthly and characterized elemental characterization was done by the energy dispersive X-ray spectroscopy. And also the effect of the outdoor PM2.5 exposure on bacterial species such as the E. coli and and Pseudomonas aerogenes, which is the related about the hospital infections. So we assess their bacterial activity and biofilm production under inflammatory and normal lung fluids condition. Again, we measured the average PM2.5 mass concentration by the month, and we started the sampling during the pandemic, actually, November 20 and till the October 21. And average mass concentration collected in Istanbul was measured as a 23.9, and there's little bit varying responses in this mass concentration, and higher mass concentration are measured between December and March, and it is expected since the industrial or winter conditions. And also we analyzed these samples elemental characteristics, and the order of the elements was the fluorine, oxygen, carbon, silicon, aluminum, barium, potassium, zinc, and calcium. These elemental characteristics indicates that the calcium, carbon, oxygen, silicon, and fluorine is dominated elements, and other elements such as aluminum, silicium, potassium, calcium are most abundant and usually related to both lithogenic and anthropogenic impact. Because aluminum, silicium, and calcium particles are also come from the construction. And we also calculate the oxidative characteristics of these samples using the elemental ratio. Main elemental ratio is the oxygen to carbon ratio, and that indicates the particulate oxidation and deformation. And also it is significant on the surface oxidation and also living system aggregation, such as the bacterial aggregation. So we calculate the oxygen to carbon ratio. And as you see the figure, the higher oxygen to carbon ratios compared to our average value were obtained in the PM2.5 samples collected between December to March and July to September. These results indicate that especially higher response on the oxidation characteristics can obtain to July to October, and it's about the photochemical reactions can be impacted on the oxidative potential. So to understand this impact on the oxidative potential, we also explained their impact on the biofilm formation and activity response of the E. coli and Pseudomonas aerogenes. The biofilm production of E. coli showed the lower level with under ALF conditions compared to the control condition, except it's the March. In addition, biofilm production of the E. coli in LAF was higher in March, April, and September compared to the monthly average. Also, more E. coli biofilms formed in the presence of the PM2.5 samples under normal lung conditions rather than the control conditions. And December, February, March, April, and July, more biofilm produced. The different responses under various lung conditions can be originated, as explained before, its major conditions, because the different pH and different ionic levels in this media. And also another tested species is the Pseudomonas aeruginosa, which is the main hospital infection and inflammatory infection, and showed different response to the E. coli under inflammatory conditions. And the results indicate that the outdoor PM 2.5 samples under normal lung conditions triggered the biofilm production of the Pseudomonas aeruginosa. So similar results obtained these conditions. Different from biofilm production, viable responses are limited under these conditions in the presence of the PM 2.5 samples, which can be normal because when the bacteria under harsh conditions or unwanted conditions, they killed or they inhibited and they produce the higher biofilms. So higher biofilms and lower viability can dominate or can explain this behavior of the bacteria. So these results also explained by the oxidative characteristics of the PM 2.5 samples. Since bacteria can limit the activity under harsh conditions and form this biofilm formation. On the other hand, Pseudomonas aeruginosa in the presence of the PM 2.5 and under normal health condition has greater activity compared to the control conditions. But also this is a good agreement with the limited biofilm formation under this condition. All these results indicate that the impact of the biofilm formation of the bacteria and impact of the PM 2.5 oxidative characteristics. And also these studies cannot explain the or examine the oxidative characteristics of the PM 2.5 samples. So all these results indicate that the impact of the PM 2.5 samples of human health and its composition impacted the bacterial responses, and it select the bacterial response according to the PM 2.5 oxidative characteristics. And thank you.
Thank you very much, Aslı Baysal. I'm very sorry for my technical connection problem now we solved. So you kindly started this next paper without any interval. Thank you very much again for your papers and your kind efforts. Thank you. Now, the third paper will be presented by Professor Ülke Alver Şahin. The title of the paper is Airborne Nanoparticulate Matter Size Distribution and Sources in the World. Please, Professor Şahin.
Thank you, Selahattin Hocam. Good to see you. I am Ülke Alver Şahin from Istanbul University, Engineering Department. My presentation is related to the airborne particulate matter. I want to show first the particulate matter general information, chemical composition or the physical properties, and then I want to explain some details in the word as an example of Delhi, and then after at the end of my presentation, I can represent in Istanbul particulate matter properties. Please.
Next one. I think it doesn't work, so please let me change.
Maybe you know, maybe you don't know, because as I can see here, meteorological student is here mostly. Airborne particulate matter is derived between nano size to 100 microsize. It's very large size distribution. But we know as a parameter PM10 and PM2.5, because these two parameters related to mass concentration has been limited all of the world for general environmental agencies. Please. Airborne particles in the atmosphere generally being primary aerosol or secondary aerosol. It occurs two ways, primary or secondary. Primary aerosol generally comes from directly source. Secondary aerosol not comes from directly source. It's occurred in atmosphere during the photochemical process, during the condensation of some pollutant gas, or coagulation or accumulation process. Particulate matter has included most things. Important one is chemical properties. There are most chemical species in the particulate matter, such as sulfate, such as nitrat, such as organic matter. And main chemical component may come from wood burning, may come from oxidation of sulfur dioxide, may come from crustal element, may come from soil dust. Major component composition of PM varied location by location. It is important to analyze this chemical profile because we need to know particulate matter species, chemical profile to mitigate, to apply mitigate policies. So if you look at the some location, roadside, urban background, or rural site, it is important that when we move the roadside to rural site, the secondary contribution, sulfate, nitrat, organic matter, such as, getting higher when we compare the roadside side. When we look at the roadside side, organic component or road dust or cluster component increasing. When we go to the rural side, secondary particle component definitely increasing. If you look at some cities, chemical composition, first of all, you can see the amount of particulate matter is very different. If the circle size, if you focus on the circle size, London PM 2.5 concentration is very low. Delhi PM 2.5 concentration is increasing more than 100 microgram per cubic meter. On the other hand, the composition is changing. If you look at the Delhi data, organic matter, Delhi and Asian data, it is in the Asian side, organic matter is very important. Second is elemental carbon is very important, and the soil mineral dust very important. In contrast, when we look at London,
Secondary particulate matter is very important. Crustal or soil dust not important in the London, especially in the Europe side. If you look at the ultrafine particulate matter, it is lower than the 100 nanometer. Shipping activity and road transportation is very important ultrafine particulate matter source in all Europe. If you look at the trend of PM2.5, it is important for us because while the Europe side PM2.5 trend decreasing in Asian sides and also including Turkey is increasing the PM2.5 concentration trend. So it is important that we need to focus PM2.5 final mode of particulate matter. This is the informative slide. If we compare the 10 micrometer particle to 100 nanometer particle, they are different mass, different surface area, different particle number. At the same volume, if at the same volume we can see one PM10 particle. At the same volume, we can see a million particle number size 100 nanometer. Surface area also very high in ultrafine particulate matter. It is important because health effect is very important ultrafine particulate matter. Currently, maybe last 10 years, all scientists focus on the particle size distribution because particle size distribution is more reflecting the climate change, more reflecting the health effect of particle. Because we can inhale finer mode of particulate matter, not coarser mode of particulate matter. If we look at the size distribution, they say more things. Number size, we can proceed number size distribution, we can proceed surface size distribution, we can proceed mass size distribution. Particle number reflect particle generally below 100 nanometer. Particle surface area reflects 50 to 1 micrometer. Must reflect generally more than 100 nanometer. It is important to what size we can focus. I want to go this slide, please. I would like to show our paper, some parts, not all. It is important because the first study in Delhi, detailed study in Delhi, particle number size distribution, we aggregate all particles. We count particle nanometer to micrometer, 10 micrometer, and we aggregate all particle 5 fraction, please. The graph reflects many things, but I would like to summarize it. When we look at the winter season, in the winter and autumn season, it's the season the people burn some more things, some crops, some fossil fuel, some biomass burning like that. In winter and autumn season, nucleation ITK mode is and also accumulation mode is dominated all particle size distribution. But in summer, crustal mode and accumulation mode similarly dominate particulate matter size distribution. This graph also shows this result. if you look at the number size, if we compare the number size distribution to the mass size distribution, we can see easily two modes in the mass size distribution. This is reflecting that there are two main sources of particle concentration. Please go on. This is important because we need to compare location based on particle number size distribution. If you look at the Asian side, coarser mode is dominated Asian side is in country particulate matter concentration. If we go to European side or London or UK, some cities, finer mode is dominated particle number side. It is important because the source is different. This reflecting the source profile. Please go on. Please go on. This is also important. I take this graph, other study. They reviewed all study in the literature, and particle number concentration is very high when we go to urban side. But when we go to polar side, Arctic side, particle number concentration is very, very low. But it is important that when we look at the trend of nucleation particle, finer mode particle, polar side finer mode particle, especially in the ATMOS particle, go to increase. But if you go to urban side or city center, particle number concentration decreasing trend. I created this graph looking at the literature because I want to show you comparing the before slides. All study is from European side and polar side. But if we need to compare the Asian side and the European side, because we have been in between these two sides, Delhi, Beijing, and Wuhan particle number concentration is very, very high when we compare the European side. And also coarser fraction is higher than the European side. There we are, as based on the particle PM2.5 here. Our PM2.5 concentration is higher than the other side, higher than especially in Europe side, but exactly lower than the Asian side particle concentration. This is part of our study, but it's not submitted yet. We are looking at the particulate matter concentration change.
Please, 1 minute left, please.
Okay. It is important, this graph, when we look at the green and the pink bar, PM10 concentration increments comparing to the rural side is very high at the rural side, urban side, etc. But when we look at the PM2.5 bar, there isn't any differences location by location, urban, rural, or other side is not significant differences. Please go. This is our study. This is from our study and published study. It is important that if you look at the BC trend, BC given variation, it is reflecting easily traffic pollution. But if you look at the PM2.5, it is not reflecting the same trend because PM2.5 increasing in nighttime, especially also slightly increase in the daytime. This is important because the secondary particle formation in Istanbul may be important. We don't know about it. As a conclusion, I see more, I say more things, but at the end of my presentation, there is a need to expand particle number size distribution as a part of the routine monitoring station. It is important to particulate number size distribution reflecting easily climate change, reflecting easily health effects. And I would like to inform you our two future study. One of them is will be conducted in Istanbul, together with the Istanbul municipality. We plan to collect PM filter at the 6th station, and we plan to analyze chemical profile and then PMF analyze for source contribution. The second one is a project. It is related to particle number size distribution. It is the first, it will be first measurement campaign in Istanbul. We can see how the change particle number size distribution in Istanbul. Many thanks. If you remember, I started my presentation in Istanbul photo with clean air. If you look at this.
Thank you very much. You can continue. The next paper title is Particulate Matter Number Size Distribution in Subway Stations in Istanbul. Yes, please, Professor Şahin.
Thank you. Thank you. Actually, this presentation was going to be made my PhD student Dila. She couldn't come today because of the job, some job things.
Yes, I can share. Yeah.
My title is Particulate Matter Number Size Distribution in Subway Station in Istanbul. It is part of the project, small part of the project, the big the project including much more parameter, including much more station. But I'm going to present only particle number size distribution data. This is the fresh data. We haven't get time to analyze more detail. So our objective is subway are a very important mode of commuter transportation, and more than 120 million passengers in 60 countries around the world use subway every day. Subway system is important to decrease, using the subway system is important to decrease the air pollution in the outside. Because if we use the subway system, we can't use the car or bus, etc. At the other hand, the biggest and only drawback of subway system is that they operate in confined space, which can accumulate unhealthy concentration of air pollution. This is the closed space. Recent work reported concentration of PM2.5 mass to be 4 times higher than ambient background concentration. The main purpose of this study is to examine the size distribution of particulate matter in Istanbul, some station. There are many studies published in our group. This slide is showing this paper. All this paper, including the particle mass concentration, we focused on the particle mass concentration currently, but after future projects and current projects, mainly focus on the particle number size distribution, chemical profile of the subway air. Please go on. We conducted this study for seven metro station. I will show only 2 station data here. There is some different information about station by station. All the station is very different by technical issue, by commuters number, etc. Some details maybe representing after me, my colleague Burcu. She's the project manager, and also I have not shown some detail in here. When we compare the particle number size distribution to the other side, other country, other city, it is the particle number sizes. The particle number size varies, as I said before, particle number size varies largely from nanometer to micrometer. So the measurement technique is also different. If we measure ultra-fine particle, we can use other equipment. If we measure the coarser mode particle, we can make other. We can use some other technology. So that limited study to cover all the particle number size distribution. We have an equipment, and we can measure only particle number size above the 300 nanometer. So if you compare the particle number concentrations, very varied. If we compare our before study, measuring the same equipment, this study result is slightly lower than the other study. We selected Kadıköy and Murtepe station. It is changing, particle number count changing day by day. And it's important contribution of the finer or coarser mode. In generally, in the subway air, submicron particulate number are contribute approximately 99% of total PM. If you look at the weekday changing, we can see easily in Kadıköy station, Friday and Saturday, and on Friday, on Saturday, and on Sunday, particle number concentration goes up. If you look at the Murtepe station, particle numbers concentration increasing daytime, not increasing, decreasing the nighttime. Kadıköy station, daytime, nighttime difference is very little, because this peak, especially in the nighttime peak, representing the maintenance activity in the subway system. If some maintenance activity made in the subway system at nighttime, it's affecting the particle emitted in the air, affecting all days concentration. This slide shows particle number size distribution differences. It is important to see shape differences. If you look at the number size distribution, if you look at the
Please, can I check? Okay.
If you look at the number size distribution, we can see small little peaks. It reflects the bimodal number size distribution. And if you look at the volume size distribution, its volume size distribution related to the mass concentration, we can see 3 modes. in all stations. It is important we can say, related to this shape, we can say that there may be 3 main sources in the subway station occurring particulate matter concentration. As a conclusion, average total particle number concentration change concentration. The Kadıköy station is an extreme station, and therefore the piston effect is less. As a result, it was found that the concentration values were lower at Kadıköy station compared with the Nurtepe station. Kadıköy station location is very important. The metro system using all weekday, not differences weekday by weekday, not differences daily time. In general, subway submicron particle number are contribute approximately 99% of total PM. So we need to focus maybe final mode of particulate matter in the future study. Many thanks.
Thank you very much. Thank you very much, Professor Şahin, especially for your interesting papers. Now we will back to next paper. Next paper will be presented by Dr. Barışcan Üstündağ using sensor technologies to measure particulate matter in urban, traffic, and industrial areas in Istanbul. Please.
Hi, hello everyone. I'm Barış. I'm not a doctor, by the way. I got just master's from Sabancı University in mechatronics. But I'm going to present our work on low-cost sensors, and our work is called using sensor technologies to measure particulate matter in urban traffic and industrial areas in Istanbul. This is a joint work by Aircon and Istanbul University. Aircon, I'm one of the co-founders of Aircon. Aircon is an affordable and easy to use local air pollution management solution. We are providing this to cities, institutions, and enterprises that would like to create value by measuring air pollutants in the air. So here is my outline of my presentation. I'm gonna first enter and show you a little bit introduction to air sensors and our motivation for this work. And then I'm gonna a bit mention related work in the field. And then I'm gonna show you our sensor system and the setup that we built for the collocation experiments, and then I'm going to show our results, conclusion, and the future way of work. So this is one of the regulatory stations located in Tuzla, Istanbul. Actually, currently, air monitoring networks consist of these regulatory stations that meet requirements defined by United States Environmental Protection Agency and standards of European Committee of Standardization. So in order to meet those requirements, these stations are quite sophisticated and expensive. And in order to maintain the accuracy of the data, the operation cost is quite high. But please, next slide. With the proliferation of low-cost sensors, which is quite popular in the academia, as you can see from the number of keywords in the previous years academic papers, it is much more affordable and reachable to get a low-cost sensor and to measure air quality in an area which is necessary. So these are two popular works related to low-cost sensors. The one on the left are from Brief London project from London. Those low-cost sensors are used to supplement the current pollution monitoring network. They are deployed in the field to supplement the current regulatory monitors. And the next one is from again London, from London Heathrow Airport. These sensors are deployed in the field to understand the effects of airport traffic to the air pollution. So for related work, even though low-cost sensors are quite affordable and reachable, they also propose some difficulties, which are the data accuracy. They are quite affected by the ambient conditions such as humidity, temperature, and microclimate. That is why those low-cost sensors need to be calibrated in the field with respect to the local climate. The picture on the left is by work from Arizona State University. They use local sensors and they do a field calibration by collocating those sensors with a regulatory station. So with a data collection for 1 month, they created a model with reference data and raw data, as shown the graph on the right, and they reached quite a good correlation score by calibrating those local sensors. So we also did the same thing, but we did it with our sensors provided by AirCom and the stations from the Ministry of Urbanization and Environment, and also from the stations provided by the Istanbul Metropolitan Municipality. We located our sensors in 3 places in Istanbul, which are Aksaray, Ümraniye, Tuzla. We selected those places because Aksaray represents a place with traffic. Ümraniye represents a place of urban, and Tuzla represents a place with industrial and urban zone. And for the collocation setup, we use AirCom's sensor unit. These are units that we have built and manufactured. They are quite easy to deploy. It is in a plug-and-play fashion. They are lightweight, solar powered, and they got connectivity options with cellular connectivity. When you deploy the sensor and turn on the power, it just directly connects to the cloud and sends the measurements as soon as possible. And these are the setups that we have built in Aksaray, Ümraniye, and Tuzla. We put our sensors on top of the regulatory stations and start to collect data. Next. And these are the results. Actually, the data collection started from 2019 and it is finished 2022. It is a long duration, but we just brought some data from the collected data set. And as you can see, the minimum values and the maximum particulate matter 2.5 values are quite similar with the reference and sensor. And we also calculated mean absolute errors daily and hourly, and also the correlation scores for daily and hourly fashion. So our correlation scores are quite high, as you can see, hourly and daily. So for the results, we then look for the effects of humidity and effects of ambient conditions to the local sensor. We are using a sensor that measures particulate matter with light scattering method. The sensors with light scattering method affects highly on relative humidity, but as we calibrated the sensor using the data that we collected for almost 1 year, the model represents all the humidity changes across a year. So our results didn't affect so much on humidity, as you can see here. So the colors represents the humidity levels, and the points, the x-axis represents the calibrated PM 2.5 data, and the y-axis is the reference 2.5 data. They are quite correlated and has a linear relation. So then next, I'm going to show you another effect of the local sensors from Aksaray and from Tuzla. Aksaray is a type of location with traffic. So on traffic times, as you can see, even though we calibrated our local sensors, they underestimate the particulate matter concentrations during the traffic times. And during, for instance, normal times, they are quite correlated and it follows the reference. But for the...
You may use the pointer.
Yeah. For if you look at the variation inside a year, so during the summertime, as you can see, our sensors are overestimate the particulate matter concentration, even though we calibrated for the sensor almost for the whole year. This is the effect of the humidity. Due to high humidity levels, our sensors predicted the concentrations a little bit high. So can you go this? Okay. For Tuzla, there are also contributions from the industrial sector. As the sensor that we use to measure these particulate matters and that we use to calibrate for calibration uses the light scattering method, and they take a particulate matter density built in as a constant. Due to this fact, when the particulate matter density changes drastically, like if you go to an industrial area, the particle density changes as if you are in a urban area. And as you can see here in the winter times, in the winter season, our sensors and our calibrated data are underestimate the particulate matter concentration. It is due to the fact that I just mentioned the difference between the particle density between the urban area and the industrial area, and this is its effect. So as conclusion and future work, we would like to investigate, as I mentioned, the seasonality effect in a more detailed way. So we would like to try the calibration in a seasonal manner, and then try to test the data as the seasons goes. And for the first things first, we would like to evaluate our results with extended tests defined by the Environmental Protection Agency of United States and European Commission with the technical specification documents. So thank you very much.
Thank you very much, Dr. Barış Can Üstündağ. It's a very interesting paper. Now the next paper, will be presented by Professor Burcu Onat. The title is Health Risk Associated with Particulate Matter in Subway Stations in Istanbul.
Thank you, dear Chairman. Good morning again. And I would like to continue the subway system and the air pollution subway system and the subway system PM health risk. Actually, my colleague Burcu mentioned the particulate size distribution in subway system, and I want to continue the other parameters actually. The title of my presentation is Health Risk Associated with Particulate Matter in Subway Station in Istanbul. And also, you know, actually the first operation of the underground subway system was operated in London in 1863. But nowadays we know that recently the most populated, most preferred, we can say, most preferred transportation mode is subway system right now because the comfortable travel and the short travel time, etc. And these systems also improve the urban air quality. I want to give an example. For example, during a subway strike event in Sao Paulo, and led to 45 and 60% increase in daily PM10 concentration due to extra road traffic in urban environments. So there are lots of advantages of subway system, but we can say one disadvantage also. The subway systems operates in confined space, and because of that, the loss of air pollutants can be accumulated in these closed areas. And actually, we can say the significant pollutant actually in subway environment is particulate matter, because you can see from the figure there are lots of sources of PM in this closed area. We can say there are also four main categories, the source of particulate matter. First one is a train, and the train's movement, for example, wheel contacts, the friction also important, and it produces lots of particulates, and the braking process, and the power supply material, for example, pantograph catenary system, and like that. Also, we have the EVIP emission, for example, volatilization of oil and other lubricants. And if you look at the stationary process, for example, cleaning of train wagons or the station, and also rail cutting and ballast changing, also night maintenance or maintenance of rail system or wagons, and lots of things produce lots of particulates. Also, ventilation is an important factor because we can say the two different modes of ventilation. One is natural and the second one is forced or mechanical ventilation. It also affects the particulate matter level in the stations. Also, human activities are very effective because the commuters, the movement of commuters cause the suspension of particles, and also the commuters' clothes produce particles, and maybe some staff smoking in the closed private rooms can cause the dispersion of particles to the subway environment. So also there are other different air pollutants in subway environment. For example, carbon dioxide because of overcrowding, and also carbon monoxide because the transferring from outdoor air to the subway environment. And also there are bi-aerosol and ozone from electrical emissions, and also volatile organic compounds. But we have got lots of air pollutants, but we can see the main challenge in subway environment actually to mitigate the producing of particulate matter from train movement. And there are lots of factors also that which influence the platform air quality. First one is, we can say, piston effect. It occurs the movement of train in the tunnel, the movement of air parcel actually. It makes the natural ventilation. And the other one is platform screen door. You can see here the two types of platform screen door. This one is the full type, full closed platform screen door. This is the half-baked platform screen door. Also, the ventilation system is very important because the ventilation shaft, for example, you can hear the two different ventilation shaft. This one is from, I think, from New York, and it's similar to our Şişli station ventilation shaft and on the road. And the other one from Hong Kong, I think, there is the better one because the inlet of the ventilation shaft is very upper height from the road. And also night maintenance affects platform air quality, and also lots of different factors such as train types, number of wheels, train frequency, tunnel length, and the promoter number. And health effects of subway PM, actually there are few studies about the health effects of PM. Some studies show that there is no very important health effects to commuters and workers, because if we look at the particulate matter composition of subway air, the main part consists of iron. So we can say iron is not very dangerous element, but the point is here, the other elements, for example, arsenic, manganese, zinc, barium, and especially copper and chromium is most dominant elements for evaluating of health risk. So actually recent studies show that especially the main, for example, particulate matter we can say is not specific pollutant because it includes a lot of different pollutants. So we can actually evaluate the other characteristics such as the oxidative potential of PM maybe is most related to health effects of subway particles. And this is studies actually start to working on it. And this is our study, and actually our first study conducted by our group, conducted in 2007, and this was conducted on only two different flights, N1 and N2, and this study conducted in this year, and our measurements actually has just finished, and my colleague said that the results are very fresh right now, and we are working on it. But I would like to give you some preliminary results of this study. Actually, we measured lots of parameters here, you can see, and the PM10, PM1, PM2.5, ultrafine particles, and carbon dioxide, carbon monoxide, metaanalyzing, also ECO, CDC, and lots of parameters we measured. But each station we conducted on 4 different M2, M4, M5, and M7. but I want to give you here only M7 and M4 lines for Nurtepe and Kadıköy station. We choose this one because I told you it's very fresh results. And the difference of these two stations is the M7 subway line opened in 2020, and the M4 line opened in 2012. And the biggest difference, actually, in my opinion, the M7 line, Nurtepe station, has platform screen doors, full platform screen doors, and Kadıköy station has no platform screen door, and both of them is the first station of the line, and the depths are not very different. I think Kadıköy station has 32 meter length depth, and Nurtepe station 35 meter length. And Hatris methodology, actually, this is the basic methodology developed by EPA and the IRIS system, integrated risk formation system. Actually, we can say this method only evaluates the particle bond elements risk assessment. So we use the elemental analysis results, and there is a formulation, the exposure concentration, and the exposure time, exposure duration, exposure frequency, and we calculate the two different parameters. First one is hazard quotient, and the second one, total cancer risk. And we used to exposure time, considering the 10 minutes, 30 minutes, and 16 minutes, because we want to evaluate the commuter exposure in the subway platform. So the exposure time is not long, very short, and in literature also studied like that. And we choose these three different time periods. And to look at results, first the PM10 results, levels on platform. You can see here, the red one is Nurtepe station, and the blue one is Kadıköy station. You can see here the PM concentration in Nurtepe is higher than Kadıköy. If you look at the concentrations, PM10 is 173 microgram per cubic meter in Nurtepe, 118 microgram per cubic meter in Kadıköy station. Also, we measured the PM concentration inside of the train, and you can see the inside train very lower than the platform if you compare between this different environments, because inside the train the air conditioning system is present, so it's actually air conditioning system prevents or we can say to collect the particulate matter inside the train, so it's lower than the platform. And if we compare the other versus subway station, there are very variable actually. There are very extreme values also. For example, in Stockholm, you can see 480 microgram per cubic meter in station platform. Also in Taipei, you can see 16 microgram per cubic meter concentration. They are very variable. And if you look at the chemical composition of the PM10, and the highest element here, iron, at both stations. And there are lots of elements, and we analyzed, I think, 23 element analysis, but the highest one is iron. And if we look at the ratio of iron and PM10, we can say 44% of PM10 in Nurtepe station consists of iron. And also we look at the Kadıköy station, around 30% of PM10 in Kadıköy station consists of iron. So we can see that actually most of the PM10 consists of iron, because the iron actually in literature also is the, we can say, subway metal, because there are lots of sources. This was the subway environment. And the iron concentration also is, I look at from the ratios.
1 minute left, please.
Yeah. And this is the health risk results, and I can say we calculate formulation according to formulation, two different value. First one is hazard index, and the second one is carcinogenesis. We can say that for both parameters, the values are below the acceptable limits. But the main thing actually, this risk assessment calculated or evaluated only the particle bound metals. So conclusions, we can say the chemical composition of the particles inherent in the subphase system is completely different from the outdoor particles. There are no excessive legal controls on our air quality, no legal standard also for the subway environment. And pancakes screen system can be prepared to prevent pre-antenna accumulation station. And these health risk values calculate at both stations are below the acceptable limit value. And future study actually the better way, I think, to evaluate the oxidation potential, the better indicator of sub-APM for health risk assessment. Thank you.
Thank you very much for your timing. The last paper is investigation of PM 2.5 levels in different indoor environments of a university campus. Will be presented by Gönenç Özarlı or anyone.
Hello, I'm here, but how can I present it?
Okay, please continue. Thank you very much.
Excuse me. Hello, this is Gönenç Özarlı. I'm just a new graduate. This is investigation of PM 2.5 levels in different indoor environments of a university campus.
Gönenç, sorry, you can duplicate maybe screen. We see black part of this.
Oh. So sorry, I'm trying to make it work, but can you see now?
Yes, it's okay.
Thank you. Since people spend most of their daily time in indoor environments, approximately 80%, indoor air quality is even more important. Poor indoor air quality may have adverse effects on human health and can also reduce operating performance. Universities are among the environments where students spend at least 1/3 of their daily time. Based on the indoor air quality, the daycare, primary school, high school, etc., many studies have been conducted in indoor environments where students spend their time during the day, but sufficient and comprehensive research hasn't been observed in universities. Particulate matter is among the most important contaminants that affect the indoor air quality. in the figure, you can see its size comparison with human hair and fine beach sand. In the studies, simultaneous indoor and outdoor PM2.5 measurements were carried out in various environments such as canteen, classroom, laboratory, and corridor, which are among the indoor environments where students spend their time during the day at Eskişehir Technical University İKEA Campus Engineering Faculty. Indoor-outdoor ratios were calculated. The results obtained were compared to the results of the measurements studied at the same campus during the pandemic period. When we look at the study area and measurement points, the study was carried out in Eskişehir Technical University in the main canteen of the Faculty of Engineering, a classroom of Environmental Engineering Department, the Environmental Chemistry Laboratory, and 2 corridors on the upper floor of the Environmental Engineering Department. The main canteen of the Faculty of Engineering is 720 meters square and has 2 ventilations. It has 5 doors facing 4 different angles, and these doors are kept closed except for the entrance and exit. At the busiest times in the canteen, approximately 100 students were in the canteen. Here you can see some pictures taken from the canteen. The classroom of the Department of Environmental Engineering is approximately 66 meters square and has 18 windows of 50 by 50 centimeters square size. Doors and windows were closed when the measurement was started, and they were opened from time to time with student activities. Classroom availability for the measurement day was 17 people. Environmental Chemistry Laboratory is approximately 100 meters square and has 24 windows of 50 times 50 centimeters square size. Along with natural ventilation, mechanical ventilation is also available. During the experiments, some of the windows and ventilation were kept open, and the door was left open from time to time due to the entrances and exits. A total of 38 people, including 34 students, 3 lecturers, and 1 laboratory supervisor were in the laboratory during the laboratory course. Here you can see pictures from the classroom. And here are pictures from the Environmental Chemistry Laboratory. 2 different corridors of the Environmental Engineering Department were measured. In the corridors, there is generally constant activity during the day. It is used for the purpose of passing from different departments, even though the available hours are decreasing during the course hours. At the same time, windows are left open all the time in these corridors, which are frequently used due to the canteen located on the lower floor. Since there was a quiz for a 90-student course in the corridor 2, the mobility between courses was higher than in corridor 1. These are the corridors. On the left side, you can see corridor 2, which the quiz was held, and in the right picture, you can see corridor 1. As indoor air quality parameters, temperature and PM2.5 concentrations were measured simultaneously in indoor and outdoor environments. While digital thermometers were used for temperature measurements, dust track 8530 aerosol measuring device was used for PM2.5 measurements. 1-minute measurement data were obtained with devices. The measurements were carried out simultaneously in the indoor and outdoor environments during the time the students were in the indoor environments, taking into account the time periods they were active in the environments. Since the aim of this study is to observe the exposure of students, academicians, and working personnel, the measurement times and periods were also different due to the measured environment. Here you can see the graphs of average PM2.5 concentrations. In the left graph, it is the Environmental Chemistry Laboratory indoor results. The highest concentration is around 1 p.m. with 565 micrograms per meter square. This is probably because of at that time, the class was ended and students started to move out. And at the same time, air ventilation, the mechanical air ventilation was on until that time, but just before students start to move out of the classroom, move out of the laboratory, the air ventilation was closed, and that's probably how such a big concentration was measured. And here you can see canteen concentrations. The highest concentration was measured 215 micrograms per meters cube. That was around 1 p.m., almost 1 p.m. And you guys, you can see that was because that was the most busy time of the canteen. When we look at the classroom concentrations are very, very low regarding the other two. That was probably, well, our guess is that was because of the classroom is a small classroom, and there was like 17 people at most, and since it was ventilated thoroughly, concentrations were not really high. And here you can see concentrations of PM2.5 concentrations of corridors. In the first corridor, the highest concentration is 39. That's really not that big of a deal. And in the second one, it's also not a huge concentration. It's 41. And here you can see a comparison with study during COVID-19 lockdown period. There was during the I'm so sorry. During the COVID-19 lockdown period, the determination of indoor air quality was carried out in the same indoor environments in the university campus by Butt et al. In the figure, you can see the results of the study were compared with the study performed by Butt and his friends. When we look at to the graph, we can see that laboratory is much higher. It's twice even. In the canteen, once again, it's 3 times more. And when we look at the classroom, it can be seen that in the COVID-19 lockdown period study, it is much higher than our study. And you can see the same for the corridor. And here you can see the indoor-outdoor ratios. In the laboratory, well, the 2 highest average concentrations were measured at laboratory and in the canteen. And you can see that here. In this study, PM2.5 measurements were carried out in various indoor environments at the university campus where students spend part of their daily time. The highest average indoor PM2.5 levels were measured as 121.34 micrograms per meter cube in the canteen and 124.07 micrograms per meter cube in the laboratory. Especially high concentration values encountered in the laboratory and canteen pose a risk for the students, lecturers, and other employees and create a less comfortable working environment. This reveals that some measures should be taken to improve the indoor air quality in these environments. While it is possible to experience effects such as throat irritation, headache, and fatigue due to short-term exposure to air pollutants, long-term exposure can have much more serious health consequences such as respiratory diseases, heart diseases, and cancer. All the indoor environments having poor air quality can be made much healthier with better ventilation and regular cleaning in order to minimize these risks for students and anyone who spends time indoors and to provide them with a more comfortable workspace. In addition, regular cleaning of the ventilation filters is an important issue in this regard. Like I mentioned at the beginning, this was an undergraduate thesis carried out using the infrastructure of Eskişehir Technical University. Thank you for listening us.
Thank you very much, Dr. Özdemir, for your timing and interesting paper. We finished the 7 papers in this morning session in air pollution modeling F1. Thank you very much for all speakers and all attendees. Now, we are going to coffee break. Thank you very much again.
Sonraki sunumda
Hello everyone. I am Funda Bostancı from İstanbul Üniversitesi. I lead the section 2. It is upper atmosphere. We have 5 talks. First one will be given on a shutter from the Atatürk University. The title is Establishing and Commissioning of the Meteorological and Astronomical Monitoring Tower in Eastern Anatolia Observatory Site. You have 15 minutes, you can start when you're ready.
Thank you. Welcome to the second session. Somebody will be very high in this project. Basically, we try to be an international observatory, not an observatory to serve the whole world, the whole community. And we try to be competitive and innovative, and so on, those people. But we do not put these words on the wall only. We try to do that with our other projects. We try to attend international meetings, and we try to make some collaborations with so many different institutions. Here you can see it from the beginning. It was only a hill, a summit close to Erzurum city. And the altitude is 3,170 meters, which is very good for air population, higher than some altitude. And you can see there in the winter time, the winter is harsh in Erzurum, especially in that altitude, but it is very good for astronomical observations. The colder it is, the more stable atmosphere. So it means a better observation in the astronomical sense. This is a photograph from the very recent time. Here you can see our tower. So this is our telescope. In this photo, it's in Italy, in Capri. Now it is established in our dome. It is a 4-meter telescope, which means it has a main mirror. It has 3 mirrors. It has a main mirror of 4-meter diameter. The bigger the mirror, the dimmer you can see, the farther you can see in astronomy. So in this tower, the aim is, maybe I should say that before here, the aim is to observe atmosphere, because atmosphere is a hurdle we need to pass to do astronomical observations, because we are observing celestial objects in space, and atmosphere is it's like a curtain over us. Actually, we would like to be in space for perfect astronomical observations, but when you are in the on Earth, you need to know the atmosphere to be able to take out its effects on your observations. So this tower does that. How it does? We have few different instruments, meteorological instruments and astronomical instruments. For meteorological instruments, maybe you are more familiar. We measure basic meteorological conditions, temperature, and that's it. With astronomical instruments, we have a few again. We have two low-sky cameras. These are new cameras, long cameras. We observe the sky all the time, 24/7. And from this, we can do so many things, so many things. Other than that, seeing monitor is probably something new for you. Seeing is the, how to define that, is the total amount or total effect of atmosphere on astronomical observation. When you take a picture of the sky or a star, it is a point result. But because of the atmosphere, it's bigger in a sense, and plus some funny things. So for this seeing monitor, we can measure that and take it out of our observations. And the TPS, turbulence profiling system, which is we are using nowadays. It's actually the main star of this show, I can say. We are carrying out the two projects, which I'm the PI. With this project, we are doing this. I will go in detail. If you can look at one, somewhere else, it's not. These are meteorological instruments. Some of them maybe you know, Vaisala and some cloud sensors, somewhere here, you can see in somewhere winter. And we have a GNSS station, which we reduce PWD crystal water vapor from this GNSS measurements. It is very important in infrared observations again. So whatever we measured here, actually it is an effect for astronomical observations. So when we know the effect, these are our astronomical instruments. These two are the all-sky camera, which I talked about. And this is the seeing monitor again in winter. And this is the TPS, what we call TPS system. It's a usual astronomical telescope. We have two of them because we have two different ways of measuring atmospheric conditions, especially two glass profile. Those are masking and jigging, what we call. And this is the end result. We have a web page. For now, it's just for internal use for us and personnel, but in the future, when we finish the project, it will be a public web page. And from this web page, you can see whatever is the condition now, or you can use that for data download in the old page. So this is basically what we do with this. Maybe I can go in a little bit detail. So, as I said, we are observing the condition of the atmosphere. By the way, I forgot to keep the time.
we are observing the atmosphere. Why we do that? In the main telescope, the dark telescope, we have something called ATMOS'22. It is an focal plane instrument. With the telescope, we observe this star, celestial object, and it's, as I said, atmosphere affects that. With this adaptive system, after we focus with light with telescope before the camera, it has some deformable mirror. It's actually something mirror. Behind that, it has 400, more than 400 pistons, electron pistons. With that pistons, it changes the shape of the mirror. So why we do this? Because if you imagine light is coming from the celestial object in space, it goes spherically, as you know. When it reaches the Earth, it has a wavefront which is totally flat. But with the atmosphere, 2 plus affects this wavefront, so it becomes something like this. And when we measure that, with this deformable mirror, we can make the mirror in the inverted shape of this wavefront. So when it reflects, it becomes flat again. But not perfectly, but we can do it up to with this with our optics. It would be like more than 90%, even sometimes depends on the conditions, 95%. So what does this mean? It means we will be as if we are in the space. We will remove the atmospheric effects 95%. So for this, we need these measurements. So with this tower, Mount Tower, we will do this measurements and we will clean our estimated observations. So basically, this is what we do. We are still building the tower. The methodological instruments are working for years. Astronomical instruments, some of them are working for years. Again, the telescope itself, we are working for our small dome. Probably in 2 weeks, we will finish it. It's about to arrive very soon. And after that, we will be able to do astronomical observations as well. I think this is all. If you have any questions, I can have some time.
Yeah, exactly. If you have any comment, suggestion, or question, you can have it.
And then what methods are using to filter the signal? That we do some kind of mirror. So what is it exactly you're using methods?
Adaptive optics system here has been developed. The adaptive optics system consists of the main part is the deformable mirror, as I said. And when the light shines on it, as I said, we change the shape of the mirror. I forgot to say 1,000 times a second, so 1,000 hertz, which atmosphere is around 100 hertz, so faster than that. And after reflection on that mirror, we see the light almost flat, the wavefront. So it is in very short term, basically taking it. But of course, behind it, there's so much mathematics going on, which I don't know the details. The result is there in the after this post, maybe you can see details is working on the system.
Thanks to Onur Çakır for the nice talk.
You're welcome. I can hear you.
Our next speaker is Recep Balbay. He is also from Atatürk University. His title is Mapping of Astronomical Observation Types over Turkey and analysis of AOT at Eastern Anatolian Observatory values from humid sensing cloud data. You have 15 minutes. You can start.
Hello everyone, I'm Rajiv Mohammed. My home, I work as an astronomer at Spark, astronomical observatory. So I give a short program about our last work, with our here. It's about actually it's a new kind of GEs. These techniques, we use the image of the satellite microsat data, and then we combine it for the astronomical usage. My introduction is as you know, the multi-factor guarantee for situation that is is the upper atmosphere actually, which is light from the telescope that causes when you have the ocean light of Earth. Actually, although the atmosphere is crucial and preparing astronomical some instruments sometimes for the high quality astronomical data. The first methodological parameter for astronomical observation is the cloud condition. If we know the sky, we can see cloud information, cloud types, clouds. As the simple methodological parameter for the astronomical observations. Also, cloud that provides long-term quality sites. Why we do archive in another or another speed and another altitude. Actually, it's very important data for question. The aim of motivation of this work actually developing a new method by cloud products from the microsat data. Which we call the astronomical observation type, unique type, actually. As you know, the metrosat satellite data generates various data sets about social testing, which we use the metrosat data in study. And as you know, the metrosat satellites have several instruments, several sensors. Two cloud products, cloud mask and cloud type, were jointly used to describe the astronomical product, which we call astronomical clearness index. Then we use a new index, ALT, for clear days of Turkey and that side for determine. By using a new real-time CMA cloud and cloud type products, instance clearness index values and the astronomical observation type days, how the difficulty was produced. Also, long-term observation type of methodology obtained and calculated by these values. The next part of the study is case analyze compact size. I will show them later. You can see these Turkey for the last side. You can see the elevation of this figure and the rocky corners of that. The Cloudmass data for you shortly of these data. Actually, we used this star tower for 3 years, 2008 to 2021. Cloudmass data actually serves to use cloudmass knowledge, which is the cloud areas, the several remote
sampling data, such as personal water report, surface temperatures, or X-ray limitation. You can see actually in this map here, there are pixels with the pixels actually, like the green plot 3, 2, or the numerical plot component like this. Also use the plot type data for the as an input and incremental product and last product for the forecasting. Actually, that type data actually includes a lot of another pixel values. We can see, we can read them in the focus table. And actually, we combine the cloud mask, CMA data, and growth factory data to create a new astronomical maps. The method actually we eliminate daytime data without the astronomical observations. We observe that fact. It is simple this. Yeah, and we don't need the daytime data for the forecasting and the knowledge of the next images. So we eliminate them. Astronomical global activity is at minus 18 degrees, which is the sunset after, I guess, or actually takes the period. You can see this table, we combine CMA cloud mask data and we convert it into astronomical cloud mask and also CT and ACT. Then we give it a name actually. Actually, we put some log, we build some logs of loss of pairs. If the ACMA and ACT is blah, it's automatic. Yeah, we define some conditions like horizontal. Cloud products are 15 minutes temporal resolution and preparing determinants of the type of data observation. Additional data observation, different angles, heights with the telescopes in the observatory. It's necessary to perform operations of a larger area and avoiding single pixel. For these two reasons, according to pixel power lifetime and larger area covered sideways, so it was considered. The telescope's plan observes its angle, which is 0 up to 7 degrees, or the maximum 200 degrees from horizon. The telescope will observe from peak of that side, which is characterized with here. Telescope will observe like an inverted cone shape, which is the upper of the focus, which is the 9,000 meters. For the imaging, like this cone shape, I put an image here. You can think actually maximum range of pixels on the telescope camera field was like determined, and high of purpose story from Parkaya, as I said, 9,000 meters, and the ATMOS stable form for the this farm actually 50 kilometers. One take maximum 10, which is 0 degrees. Pixel width for metals damage actually is in that region, like 5 kilometers. According to this information, the spawn base contains actual and hypotheses for metals applications. We used actually nine hypotheses considered from that side. As I said, we put loss of if the casing, case selection, if 50 or more persons AC values are 2, in this case, these are defined by automatic. ALT actually is here under absolute convolution type, and the AC is here absolute variance index. If we AC values of these images if the 40% or more for good case, we call it the spectroscopy and level 1. If the AC values of this 6 doesn't meet the multi condition, the area becomes as unavailable for 0. According to criteria, even produce light next step after resolution type area that's set determined or what type of resolution we make to get time, which means actually we calculate if 50 or more person are calculated for plasmids during the night, we define the last night as automatic, right? And it goes on. Examples of the DNAs which we study, we can see cloud mask, cloud type, and which recorded the ALT images from the whole micro of these. Also, we study the log time for Turkey. You can see these images figures. First one is automatic. Second one is spectroscopy, and we combine the total. You can see that here, also produced quite actually very good spike, or we can prove these works from this study. Distribution of the values on that side, the automatic aspect of almost 80, actually smaller than 7%. This study will develop contemporary products with all cloud data. Concept of astronomical observations that needs of astronomy and astronomers. It will have to produce products developed for the another groups. It will be easy for astronomer to use these maps which you create instead of cloud products or astronomical, and it will make more accurate to see it. Additionally, valuable infrared or radio observation methods are considered as innovative, expanded, and multi-study. When to improve our methods using the data set in the future. To sum up, we in the study new astronomical formats which we call ALT, and they all several observation, Turkey, and the number of observable days on the website and the long-term observation cycles of Turkey or calculating values. Additionally, methods of study can be developed at a custom observatory anywhere on Earth. Thank you for listening.
Any comments and questions? Okay, thank you very much. Next speaker is Ahmet Polatoğlu. His talk is about Turkey's first cosmic ray measurements in Antarctica. Ahmet, can you hear us?
Yes, I can hear you. Can you hear me?
Ahmet, can you hear us?
Yes, I can hear you. Hello. Hello.
Hi, Ahmet. You have 15 minutes. You can start.
Okay. Hello, everyone. I respectfully greet all participants. My name is Ahmet Polatoğlu. I am attending from Atatürk University Astronomy and Space Science Department. Today, I will present to you a topic that is part of my ongoing PhD thesis. The title of our topic, Turkey's first cosmic ray muon measurement in Antarctica. I prepared this study together with my doctoral thesis advisor, Professor Dr. Cahit Yeşilyaprak, my co-advisor, Professor Dr. Mithat Kaya, and Dr. Onur Şatır. The content of my speech is as follows. First, what are cosmic ray in brief? What is the background of the project? Second, what does the materials used and the experimental system consist of? Third, method and data analysis. Fourth, research findings and discussion. Fifth and last, conclusion. In this way, I will complete my presentation. Cosmic rays are high-energy particles that include 19% protons, 9% helium, and remaining heavier elements, electrons, and photons. They come from the Sun, Milky Way galaxy, supernova, and active galactic nuclei. High-energy primary cosmic rays start to collide with atomic nuclei in the upper atmosphere, nearly 35 kilometers above the ground, producing massive shower air with up to 10 billion secondary particles. The resulting secondary cosmic rays consist of many particles, especially pions. Charged pions can decay rapidly by emitting particles called muons. Unlike pions, muons don't interact strongly with matter. They travel through the atmosphere to penetrate underground. Muons are charged elementary particles with high energy and strong penetrating properties, with a mass of about 200 times the mass of electron. Cosmic muons are detected by coincidence between two scintillator tiles placed in a tower. When a charged particles, mostly muons, penetrates these tiles, they primarily lose their energies by the ionization process. More generally, particles such as electron, gamma, radon, and muon can be measured in the scintillator, but it is as well known fact that muon from cosmic rays is measured nearly 95% at sea level. If we talk about the project process, we designed and set up a scintillation detector at Atatürk University in Eastern Anatolia Observatory project, DARC project, within the scope of my doctoral thesis. Detector's first tests were carried out in Erzurum DARC location, and the operation of detector was confirmed. Later, the designed mini muon detector was sent to Antarctica for measurement. In the scope of TÜBİTAK Polar Research project conducted by Dr. Onur Şatır, and Dr. Onur Şatır took the measurement 16 days between 10 and 25 February 2022. The results obtained were compared with DARC, Erzurum City Center, Mersin, and similar studies result in the literature. Another purpose of ours is to make a cosmic ray flux map by making measurements at different points. Now let's talk about the components of the experimental system. The cosmic ray muon detector system designed in the study consists of different elements, two scintillator plates, two photomultiplier tubes, a signal reading system DRS4, SMA BNC cables, power supply, computer, and a tower. The scintillator plates used are a plastic scintillator measuring 5 × 5 × 1.5 centimeter in size. The scintillators show maximum sensitivity at a wavelength of 420 nanometer. Hamamatsu photomultiplier tubes are 2 × 2 × 5 centimeter in size. Detectors work with 5 volts. For convenience, the power inputs are designed to be supplied via USB from the computer. This scintillator and emit lights. This light is transferred to PMT directly connected to the scintillators. The photoelectrons that detached by these lights hitting the cathode of photomultiplier are multiplied by PMT and sent out as millivolt. Afterwards, the signals are directed to the DRS4 device and converted to digital. A cosmic ray passing through the detector above and reaching the detector below is performing a count on DRS4. These digitalized counting signals are recorded by the DRS4 oscilloscope program and prepared for analysis. The method used the time of flight method. The TOF method consists of detector placed on top of each other and spaced d apart. When the cosmic ray passes through the detector above and reaches the detector below, the flight time in this range is calculated. In the cosmic ray measurement seen in figure, the yellow curve, channel 1, shows signal coming from the first scintillator, and purple curved second channel, 2 point where the two curves start to slope downward. T1 and T2 are determined with a code written in Python. T2 minus T1 value is equal to TOF value. All TOF values calculated and recorded at a text file. Well, with the obtained TOF value, a histogram is created by the root analysis program. The mean, TOF, and standard deviation are important parameters by drawing the appropriate Gaussian curve on the histogram. The cosmic ray muon flux is calculated using the data obtained and the measurement in the experimental system. The essential feature of muon flux measurement are integral and differential density. Flux density is defined as it is number of particles per unit area A, unit time T, and unit solid angle omega. Equation 2 is used to calculate cosmic ray muon flux. TOF values were obtained by analyzing the measurement results. Histogram was drawn in the root program with TOF value. Gaussian model was applied in histogram. The mean value was found to be 0.825 nanosecond as shown in graph. When a cosmic ray passes at a distance 27.5 centimeter at the speed of light, light, the average flight time is calculated as 0.9 nanosecond with equation 1. The result found agree with the theoretical value. The standard deviation was found to be 1.19. As a general statistic on the histogram, the mean plus and minus 2 sigma range corresponds to 95% of particle. This value is equal to the total number of cosmic muon rays measured. In this equation, phi is cosmic ray muon flux, n is number of particles, d is the distance between two detectors, a is the surface area of a scintillator, and t is total time elapsed. The error is proportional to the square root of the total number of particles. Calculated the muon flux density obtained with 16-day measurement is 0.0164 particle falling at a steradian angle per square centimeter per second. Measurements were also made in DAG site and Mersin seaside. According to the result obtained, the cosmic ray flux density of Erzurum DAG location, 3,170 meter altitude region, was found 0.0458. Erzurum city center is 0.0238, and Mersin sea level we find 0.0136. The flux rate found was reported in the literature, Asatiani et al., and presented in graph. In other studies, measurements were made at different angle, cos theta of the detector. The angular distribution was not examined in this study. Measurements were made only for theta, 0 degrees, with the detector placed vertical to the sky. According to the measurement results, the flux at 3,170 meter altitude is about 3 times higher than flux at a sea level. The most important parameter for cosmic ray measurement is altitude. However, in the study, we want to look at the flux change regionally. At the same time, when the Antarctica and Mersin value are compared, the flux in Antarctica is higher. This is related to the structure of magnetic field lines. Cosmic ray ratios vary depending on latitude, longitude, altitude, solar activity, and extragalactic activity. In general, the results agree with the literature. Conclusion and future goals. In this study, muon flux measurement was made with a cosmic ray detector in Antarctica for the first time by Turkey. DAG studies are carried out in Erzurum. However, within the scope of the polar projects, the establishment of science bases in the poles of Turkey and conducting observational studies are important in order to have a saying in the field of science. Measurements will be made at different latitudes and longitudes, and the cosmic ray station will be set up that continuously receives data in the DAG sites. In fact, detectors that have been receiving continuous data for 3 or 4 months are working in DAG site. The cosmic flux map can be drawn by measuring as much as possible at higher altitudes and in more different regions. As a result, we make an experimental observation and we will interpret the results according to these observations. Additionally, cosmic ray muon are abundant in the atmosphere the muon flux has long been used for the characterization of particle detectors. Cosmic rays also appear as noise in telescope CCD and CMOS cameras images. In order to clear these noises, the cosmic ray flux density must be known. Finally, cosmic rays are related to issues such as solar activity, climate, and weather conditions. These are the most studied topics in recent years. This study will open the door for us to work with such disciplines. I completed my presentation. Thank you for attention.
Thank you very much for the presentation. Okay. We are going to next speaker, Kambelan.
Hi.
Hi.
I'll share my screen, but I can't. Okay.
Okay. The title is Analysis of the Relations between Solar Activity, Cosmic Rays, and Earth Climate using Machine Learning Techniques. You have 15 minutes.
Okay. Do you see the screen?
Yeah.
Okay. Hi, everyone. I'm Bukem. I'm a PhD student at ATMOS'22, and I'm going to present the topic of the analysis between solar activity, cosmic rays, and Earth climate. This is actually what Mr. Ahmet Polatol just concluded about that they'll also be working on this topic. So today I will first give a brief introduction and background information, and then talk about the data and methods I used to give my results and summarize and conclude. So this is our Earth. It's part of a system, and the system is also composed of subsystems that interact with each other through physical, chemical, and biological processes. The climate of our Earth is also part of this system, and it's a very complicated structure that can be affected by many different parameters that are both internal and external. It's important to study the external forces to understand the stages that our climate has been through and to predict the changes in the climate. So this paper looks into the correlation between external forces such as galactic cosmic rays and solar activity, and the Earth climate using the parameter cloud amount. So the goal of this paper is to reveal the temporal and geographic relationship patterns by examining the existing complex data using machine learning methods. And machine learning methods are used for the first time to look at the solar influence on climate. So how are cosmic rays related to the climate? It's actually through clouds, and clouds play an active role in the control of the radiative balance of the world. And cosmic rays are modulated by the solar activity. So when the sun has low solar activity, there are more cosmic rays incoming to Earth and more low-level cloud formation. These clouds reflect more sunlight into space, and the Earth becomes colder. This is basically how the mechanism can be explained. And cloud microphysics play an important role in this. So the cosmic rays create ions that combine with the aerosols in the atmosphere, which cause the growth of cloud condensation nuclei. And these cloud condensation nuclei are actually aerosols with a diameter of 100 nanometers, and they act as a nuclei to form clouds. The link between cosmic rays and cloud cover was actually first suggested by Svensmark and Christensen in 1997. And they said that the variation of global cloud cover was positively correlated with the cosmic ray flux between the years of 1983 and 1991. Then in 2000, Marsh and Svensmark extended their analysis to up to 1994, and they said that the cosmic ray flux the correlation was only restricted to low-level clouds. In 2003, another study stated that the ISCCP low clouds was difficult to interpret because of their dependence on IR measurements. So they questioned the reliability of the ISCCP satellites. In 2004, Usoskin and his teammates used latitudinal regional averages for correlation, and they stated that the cosmic rays were mostly correlated with the low cloud amount over the mid-latitude regions. In 2007, it was showed that a region in the equatorial Pacific Ocean, the ENSO effect prevailed over the solar effect, which I'll be talking about later. And basically, it was stated over and over that the effect could be small, but it also could be important. So no definite statements has been made on this topic, and future research is required on the speculative relationship. With that, the data used in my analysis can be divided in predictors as predictors and predictants. The predictors, which are the cosmic ray flux, the sunspot number, the total solar irradiance, the UV irradiance, and the oceanic Nino index, they are independent variables that are used to predict the outcomes, while the predictants, which are the total cloud cover and the low cloud cover, are the outcomes in the models. And all of them have been used as monthly averages from 1984 to 2017. And these parameters were gathered from data used in previous research. As for the methodology, we began by first exploring the obtained raw data, and then all of the data sets were pre-processed using a 12-month moving average. This was to remove the seasonal effects. And on top of that, the ISCCP data was detrended because there was a clear decreasing trend seen in the data set. And this trend was claimed to be artificial by previous studies. Then the analysis began by trying to obtain the same results as previous studies that investigated the linear correlation between cosmic rays and clouds. And we extended those studies to the present. So the Pearson correlation coefficient was calculated to evaluate the linear correlation. And then regression analysis was performed using multiple linear regression models. R-squared values were calculated, which I will explain in the following slide. Also, the cloud data sets were either used as global or regional averages or pixel-wise global data. The pixel-wise analysis creates a different regression model for each pixel, and the results are shown as global maps, while the regional averages are, the 4 different latitude zones are used for the regional averages, and they were taken from, again, previous research. So the 4 regions are first global, which averages over the whole globe. Region 1 is averaging over the whole globe, excluding the poles. Region 2 is only the tropics, and region 3 is the mid-latitudes. And these are the metrics that are used in the machine learning models. And they're used to evaluate the regression models and to quantify their performance. The red lines shown in the figures are the regression lines that best fit the data, and the residuals are the difference between the observed and predicted values. Sum of squares total and sum of squared errors are the error metrics used in calculating the coefficient of determination, which is called R-squared. So R-squared is a good value to measure the model of the fits, and it was used in our study. Moving on to the results. These are the results of the reanalysis of previous studies. The linear correlation coefficient between the cosmic ray flux and the cloud amount was calculated for 3 different periods. And these periods, the first one was the analysis of Marsh and Svensmark in 2000. The second was of Usoskin in 2004. And the final one is our analysis period. The low-level cloud was found to be highly correlated with cosmic rays from 1984 to 1994, which was consistent with previous reports. But the total cloud amount did not have a similar high correlation for all regions. Only region 3, which are the mid-latitudes, was highly correlated. But when we expand the analysis time period, even by 6 years, there is a significant drop in the correlation coefficient. And when the time period is expanded even further until 2017, the correlation values remarkably decrease for both total cloud cover and low cloud cover. So it is seen that the correlation lasts up to maybe 1990, but then it's completely lost. And here, the comparison can be seen better. The figures above are from the mentioned studies, and the figures below are the ones we recreated. And you can see the drops occurring in the Pearson correlation coefficients when the time period is expanded for all regions. Then we moved on to the pixel-wise correlation. So here, the correlation coefficient is calculated for each pixel and then is shown as a global map. Here, first of all, the problems using the ISCCP data can be seen. Over the Indian Ocean and Pacific Ocean, there are satellite footprints, and there's also missing data that can be seen as blank over Asia and Antarctica. The regions that have high positive correlation can be seen over the mid-latitudes, over the Atlantic, Pacific, and Indian Oceans. Similarly, the regions with negative correlation can be seen, and there are parallel in both total cloud cover and low cloud cover. So from these maps, it can be seen, it's observed why taking global or regional averages can lead to low R values. Then we move on to the maps using linear regression models, pixel-wise maps. These are where the predictors are mentioned and the predictants are total cloud cover and low cloud cover. Negative pixels are shown as 0 in these maps. And such negative pixels are where the linear model fit is a poor fit. So firstly, here we can see that a majority of the pixels have negative R-squared values, meaning that the performance of the linear model is very poor. There are some strong R-squared values that can be seen again in the mid-latitudes. Using the total cloud cover, the predictant fits linear model better for the cloud product. Yes, this could be because of the ENSO effect on the Pacific, which is mentioned in previous studies. To summarize, the relations in different geographical and temporal patterns were investigated. The reanalysis of previous correlation studies was performed. The ISCCP data showed high correlation for the period 1984 to 1994, but the correlation weakens after 1995 and is completely lost after 2000. The pixel-wise correlation maps showed positive correlation in the mid-latitude ocean, which was consistent with previous reports. The machine learning analysis showed that the linear model fit was poor. The overall higher R-squared values for the total cloud amount was in the equatorial Pacific Ocean, and this is suggested to be because of the reported ENSO effect. The interrelations between the parameters was the main focus of the study, and the reasons for the relationships were not investigated. Linear relationship seems to not exist between the parameters, but a nonlinear relationship could exist. So to continue our study, we will be looking at nonlinear regressions such as random forests, and the predictive power of the algorithm will also be measured. As for the problems with the ISCCP data, different sources for cloud data will also be used, such as from the satellites MODIS and MERA. And as for further future work, research will focus on regions with high R-squared values, and possible connections that are not external could be through winds and aerosol mass maps. So these were also maps from other studies, and they will also be thought about in our future work. So thank you for your attention.
Thank you, Ms. Pika. Do you have any question? Yeah, we have one question to you.
I have a quick question. Why do you think there is a weakening and then disappearing of the connection? Is it solar activity or something else? Or climate change? I don't know.
I cannot really hear the...
Now, can you hear?
Yes, I can hear better, I think.
Why do you think the correlation is weakening and then disappearing? Solar activity, climate change, what is the reason? What do you think?
What's the reason of the correlation?
Correlation is weakening and then disappearing, you said. After 2000, it's lost. So why do you think it is?
I'm not really sure why the reason is. Probably, I believe that the found correlations between the small period was actually false. So there was no real correlation to begin with, and it was only a coincidence, maybe.
Okay, thank you very much.
Thanks again. And last speaker is Nur Sena Tepedelen.
Yes, I'm here.
Ah, okay.
I am sharing my. Okay. Can you see the presentation?
Yes, we can.
Okay. Hello, my name is Nursena Tepedelen. I am senior year student, Department of Meteorological Engineering at Istanbul Technical University. Today, I will present a part of my graduation thesis, which is about geomagnetic storm time changes in the thermospheric natural winds. Firstly, I will briefly remind you the atmospheric layers and the thermosphere, sorry. Then the sources that cause variability in the thermospheric natural wind. In our study, we used the empirical horizontal wind model to quantify the changes in the thermospheric natural wind. Thus, I will introduce you the horizontal wind model, and we will look at how horizontal wind model evolved over the years. Finally, I will present the horizontal wind model results and our findings for this selected geomagnetic storm day. Let's start with the atmospheric layers. These graphs generated for North Camp, Norway at 71 degrees north latitude using WACCMX and TIGSM models. Atmospheric layers during a quiet day on March 16, 2015, and the geomagnetically disturbed day on March 17, 2015 are shown. Thick lines refers to storm time and thin lines indicate the quiet time. Also, red lines are for ions and blue line depicts neutrals. I would like to draw your attention to the coexistence of ions and neutrals in the upper atmosphere. Here, the thermosphere starts from 80 kilometers and extends about 500 kilometers till the exosphere as seen in the first graph on the left. The ionosphere and thermosphere overlap and interact with each other in various ways. The number density of neutrals are higher than the ions at all levels as seen in the third graph. Fourth graph shows the temperature thermosphere coexistence mostly of oxygen and nitrogen molecules and also oxygen atoms. As can be seen in all figures, storm time values show large deviations from the quiet time values. In this work, our aim to quantify the changes in the thermospheric natural wind due to the geomagnetic storm disturbance. So, thermospheric natural wind is the motion of neutrals in the thermosphere. On the image left, the interaction between ionosphere and thermosphere system. The energy sources in the thermosphere which cause in the thermospheric natural winds are absorption of extreme UV radiation, Joule heating by electrical currents, particle precipitation from the magnetosphere, dissipation of upward propagating waves such as tides, planetary and gravity waves. Also, the energy sinks are infrared cooling and chemical reactions. The image on the right shows that the thermosphere is influenced both above and below. As a result of thermospheric natural winds varies according to solar and geomagnetic activity, universal and local time, day of the year, latitude, and interplanetary magnetic fields. The graph on the right shows the day and night variation, solar maximum and minimum of the thermospheric parameters over Istanbul at 0 UT at night and 12 UT for noon. The highest temperature and densities occur during storm time, solar maximum at noon, and the lowest density and temperature are found for quiet solar minimum at night for 0 UT. Because of the lack of simultaneous global measurement, we rely mostly on models for understanding the interaction mechanism in the thermosphere. Models for ionosphere thermosphere studies are divided into empirical and physics-based. We use horizontal wind model in our work, which uses historical data from radar, spacecraft, rocket probes, and Fabry-Perot informators. Mathematical feats are applied to the data to obtain statistical patterns. The most recent version, the horizontal wind model, the last row, uses data from 44 different instruments spanning 60 years. So geomagnetic storm data was also ingested in most recent version of the model. So we come to the data and methodology. To quantify the storm effects on natural winds, one geomagnetic interval and quiet day was selected our investigations. The selected interval is May 14 to 18, 2005. On 15th of May, a geomagnetic storm occurred on Earth due to an Earth-directed CME, which is coronal mass ejection. The graph on the left are magnetic fields graph. Top of the chart, B is resultant of Bx, By, and Bz. The graph on the right shows proton density, velocity of the wind, geomagnetic storm indices such as AE, KP, and DST. The simultaneous increases in all solar winds and IMF parameters indicate CME passage from the location of the spacecraft shown it with yellow lines. So this graph shows the quiet day and phases of the geomagnetic storm. KP varies from 9 to 0. If KP equals 9, denotes a severe geomagnetic storm. Also, DST smaller than -40 shows that the disturbance can be classified as a geomagnetic storm. During this geomagnetic storm, KP maximum was 8.3 and DST maximum was -247 nanotesla, showing a severe magnetic storm according to NOAA magnetic storm scale. So there is three phases of storm are shown in this figure: initial, main, and recovery phase, according to the variation in the DST index. During the initial phase, storm develops and energy is released during the main phase, and also things start to getting normal during the recovery phase. Also, AE index shows auroral electrojet activity at high latitudes. If AE bigger than 500 nanotesla is a moderate substorm. In top panel, AE bigger than 500 nanotesla at all times during the geomagnetic storm represents storm time substorms. The storm time interval between 15 and 16 May is compared with quiet day on 14 May to quantify the changes in the natural winds. Comparisons, so let's have a look at the global variation of the natural winds on quiet and disturbed day. The maps on the right shows the wind field at 130 kilometers for quiet and storm days. The gray parts areas do not see the sun. Also, for the quiet time wind, the flow is from day to night side. Changing in the temperature gradient causes the pressure gradient to change, and wind intensity increases as you move from equator to higher latitudes. Also, pink boxes show where to find the maximum changes. Intensified over North America in night sector, and the weakened wind over Russia on the day side can be seen during night storm. Also, graphic 4 shows quiet and storm time wind field differences at 130 kilometers for peak of the storm during main phase at 8 UT. On average, maximum was change found to occur 75° east during the geomagnetic storm. Thus, 75° east was selected to quantify the maximum change in the natural wind in this study. High profiles of the storm time in differences in the natural wind speed. These plots were generated for the peak of the storm at 8 UT during main phase. Altitudes of the maximum change at 8 UT are noted on the plots. At all latitudes, the maximum change was around 150 kilometers. 150 kilometers is the altitude where joule heating and auroral particle precipitation dominate during the geomagnetic storm. These energy inputs derive the changes in the natural wind. During the main phase, the largest change was found at 75°. In graph 10, as one goes to the upper latitudes, the difference in wind speed increases sharply compared to the lower latitudes. This is clearly seen. The 75° denotates with purple line. However, the response time of the natural wind to incoming energy input is different at various altitudes, so other times should also be investigated. Timing, then we come to the timing and magnitude of the maximum change in thermospheric natural wind at selected altitudes. This table shows in the what phases and what altitude the maximum differences in the natural wind peaked. The rows are for different latitudes. In every latitude zone, maximum differences in the natural wind was similar between 200 and 400 kilometers. Maximum change did not vary too much above 200 kilometers. However, 400 kilometer values are slightly higher. On the other hand, the timing of the maximum difference occurrence was different at each latitude. Equatorial maximum, though small, was during the initial phase. Mid-latitude maximum differences were during the main phase. At high latitudes, such as 75 degrees, maximum difference occurred during the recovery phase. This suggests ions might play a role in delaying the response time at high latitudes. As a summary, in the study, an empirical model of the thermospheric natural wind was run to measure storm time variations in the natural wind direction and magnitude. Overall, the quiet day results show that the horizontal wind model presented a good statistical picture in the line with theoretical expectations. Changes in the natural wind were more pronounced at higher latitudes, around 150 km for 75 degree east, due to energy input from Joule heating and auroral particle precipitation. Finally, the response time of the thermospheric natural wind was slower at high latitudes. The maximum change was found during the recovery phase. This suggests ions might be playing a role delaying the response time of the natural at high latitudes. Thank you for listening.
Thank you, Nur Teperay. Do we have any question? I think there is no question. Thanks again. This is the last topic. So we have a lunch break. Next session will start at 2 p.m. Thank you for your attendance. Gerçi onlar söylerlerse duymuyoruz galiba, değil mi?
En son çok fazla kişi yok tabii. 10 kişi yok. 5 buradaki bilgisayar var.
Ha, öyle mi? Sesi daha çıkmıyor da ben mi duymuyorum acaba? Daha çok o zaman şeyden, YouTube'dan mı istiyorlar?
Yani ondan da pek şey değil ya. Burası daha fazla gibi.
Evet. Öyle oluyor şimdi son gün olunca.
Aynen. Bir de son.
Teşekkür ederim. Hemen kendime oturuyorum. İşim benim ya, o yüzden hazırlığım yapmaya uğraşalım ben de. Ben sana şunu da vereyim. Tamam, oradan unuturuz. Artık bu saatte kimse geleceğini düşünmüyorum. Ben sana o canlı soruyu tekrardan. Başka yatırım olmuş mu? 150 lira ekstra var. Sen demiştin bu sefer işte konuşuruz.
Good afternoon. Everyone ready?
Merhaba hocam.
Başlıyor muyuz?
Başlıyoruz hocam. Buyurun.
Good afternoon, ladies and gentlemen. Our session is air pollution modeling. There are 7 different subjects in this topic, in this session. One of them is a meteorological analysis of the sand and dust storm in Konya on November 30, 2021. Prepared by Emel Ünal, Gökçen Işık, Derya Ergün, Barış Özgün, and Cihan Dündar. If Emel Ünal is ready, please continue.
Okay, thank you hocam.
Bir saniye hocam.
So I will try to present a meteorological analysis for sand and dust storm event in Konya, and I think for the humanity, if you don't see anything, you can't do anything, basically. And here is one of the example. If you don't see what can happen, it's really, really big traffic accidents and people get injured, and it was really, really bad situation. So with my friends, we will try to explain why did it happen. Okay, let's start. So first of all, general world situation for the sources of dust and sand. So we are over here and we are affected by this dust belt. More specifically, these places are like almost no rain or really, really little amount of rain, water. So it's all getting really affecting our visual, our life, our health, different parts. More specifically for Turkey over here, we get from, we have 2 sources directly affecting Turkey. This is the African part and Middle East part. And these are really wide areas. They are just basically sand or dust. They can transfer to the long distances. And according to particle size and residence time, we can tell that large particles like suspend less time, or in the atmosphere they stay less time. But for the small particles, we have more time. At least we have longer distances that they can go. So for our event, these are just general part, but for our event, we have a specific place actually, inner source. So I want to mention about the Konya closed basin. It is just a closed basin, so there is no input from outside. It is just rain for the water sources. So it is really important to see rain is coming or not. But it is getting lesser and lesser in last years, so it's getting drier and drier. And also this region, especially these parts, are really vulnerable to the wind erosion or other weather events that affects the soil. So for that reason, we have the aridity index. You can tell that this region is really, really unique in Turkey, because aridity is really affecting. And also some parts of the southeastern parts are also like that. it is like edge of Middle East actually. And that's why Konya Karaman need a park. There are some reforestation cautions, but still it's getting really desertification risk. Here also you can tell that desertification is really high over here. So basically soil is so open, you can just make it transport to the all around these cities. It can be affected because of this. And also here is the winter erosion map, and here again, same region is affected from the wind. And also when we look at the precipitation amounts, we can tell that it is also getting less and less so drier soil conditions, because like between 91 and 2020, there is really less, like almost less than 200 millimeter. For a long decade, it's really arid or really less amount of precipitation. And then for our case, we just look at the upper synaptic scale, upper level charts, and we check the EOS data, meteorology charts like surface 180 hectopascal, 780 hectopascal, etc. And we have done the analysis with the Excel and GIS, and we can see the details like weather is really convective situation, the stability is really low, and also wind parts, you can see over here, it is windy for that region that is dry and arid soil, getting more wind. And then, okay, these are the excellent results, let's say. So on 13th November of 2021, there was like a huge sun and dust storm, and visibility distance is like almost 10 meters or less, some parts. So people couldn't see what's coming and just make the accidents and have the problems. And this is the weather situation. Like the temperature difference between the surface and the upper levels is huge. There is the low pressure effects from the surface, and also really high winds through the upward vertical motion, and it makes the convectivity like through structure, it helps the convectivity occurs easily. And this is the you can see the differences between the contours. It is really for 850 hectopascals level, it is really wide, really changing small distances actually. And you can tell the winds amounts are for different times of that day. The events occur at afternoon, like around 1 p.m. But it's getting stronger and stronger, you can tell, because of the time of the day, the diurnal variable changes, and 10 meter wind speed is increasing. And when we check the stations, we can see the special distribution, especially for these. These are the places that I have shown you the dry, like desert region. So it just makes the sand upper and transport it to the other cities. Even though in Ankara we have some small effects, and not just in Konya. And it is far away, kilometers away. And you can see also the station differences for the wind speed, like in from 25-30 meter square for the station that changed in a short time. Also, we checked the long-term precipitation amount for that summer. So from June to the November part, it is all dry. Just a few small precipitation amounts that you can negligible. It can be negligible to this event. So again, same area is less amount of precipitation. And if you check the anomaly, you can see all the underestimation, lower values from the normals. So it makes it really dry. And also you can tell from the soil moisture, okay, this is a model result, but still it's a fraction. So if you see the 100 saturation, 100% saturation, so all full with water, it's like really dark blue. And if there is dryness, then it's going to be yellow. And same region, again, soil is so wet for the upper soil part, like first 20 centimeter part. So this means soil is really open to the wind, and you can just move it easily. And from the satellite, actually, we can show these movements via wind. And these pink areas showing that sand or dust from the source, from the soil, just going up and northeast direction. And then also we can check the air quality stations, and we see the impact also. And in TSMS, Surface State Meteorological Service, we have a modeling for dust surface concentration, and it's actually it's the forecast for the day, and it is seeing the region there can be something. And this is the link. If you get interested, you can check the model. And this is the concentration changes with respect to that day, PM10 concentration, and you can see this peak easily. It is from the Nevşehir. It is on the road of this dust storm, actually, with station. So you can tell it's coming a little bit, and then suddenly it peaks. And the other ones also, Aksay or Niğde, they are really close to the source. So that's why they're just getting small amount. And then the farthest away Nevşehir is getting more, because it's like a sweeping all the area and getting all the dust through the faraway seas. And these are the main results, let's say, and we have modeling with these conditions, and we are getting more and more these events. And we have also a new structure for these sand and dust storms. With WMO, we try to do the node, a kind of center for the events and their research in our region. Especially together with Iran, we will work for more research about these topics. And also, we should include that we have an inner source. We don't really get involved with the other outer sources also. So it is important for us too. Like Konya, Kırman, Aksay region is really important. We need to maybe get cautions for the other parts. And also it is an extreme condition. So even though most of the time we think that highly extreme precipitation will cause a problem, also lackness of precipitation will cause another problem. So we need to think both for the daily operational events. And that's all. Thank you for listening.
Thank you very much, Emel Ünal. You prepared good subjects As you know, the sand and dust storm from region or from Africa or Arabian region, it is affected sometimes in Turkey and some regions. Is there any questions? We can ask one or two questions. Both from online or from face-to-face. I think there is no questions. Thank you very much. Continue this kind of subjects. Now, the second subject is global and regional analysis of atmospheric aerosols, prepared by Cihan Dündar, Ali Pekin, İsamettin Omak, Gökçen Işık. I think this present from online site from Zoom. Who presented?
Yes, Mr. Chair, my name is Cihan Dündar. Do you hear me?
Yes. Microphone and screen for you. Continue, please. Thank you very much.
Thank you, dear Chair and ladies and gentlemen. I will continue my presentation in Turkish, and you will find our English version of paper in symposium book. Tekrar merhabalar. Yani kendi dilimde daha iyi anlatacağım için Türkçe anlatacağım. Lütfen kusura bakmayın.
Tabii buyurun.
Hocam ekran paylaşımı geldi mi?
Buyurun, geldi.
Teşekkür ediyorum tekrar. Meteoroloji Genel Müdürlüğü'nde çalışıyoruz. Muhammed Ali Pekin, İsamettin Omak ve Gökçen Işık arkadaşlarımızla birlikte bu çalışmayı hazırladık. Küresel ve bölgesel olarak atmosferdeki aerosollerin ama ağırlıklı olarak tozların analizi 2003 ile 2020 periyodu arasında sizlere sunmaya çalışacağım. Değerli katılımcılar, aerosol dediğimiz zaman öğleden önceki oturumda da zaten Ülke hocamız uzun uzun diye anlattı. Atmosferdeki her türlü askıda bulunan katı ve sıvı parçacık olarak tanımlıyoruz. Bunlar doğal olduğu gibi antropojenik, insan kaynaklı aerosollerde olabiliyor. İşte insan saçının 10 mikron dediğimiz, PM10 dediğimiz kirletici 5'te 1 ile 7'de 1 arası. PM1, 2,5 ya da nano boyutlarına gittiğimiz zaman yüzlerce kat daha küçük insan saçından parçacıklardan atmosferdeki bahsediyoruz. Kumsaldaki bir kum tanesinde büyüklüğünün yaklaşık 90 mikron olduğu literatürde geçiyor. Bu grafiği Emel Hanım da göstermişti. Dediğim gibi öğleden önceki oturumda birincil, ikincil kirleticiler olarak da tanımlandı. Biz çöl tozları, mineral tozlar ve deniz tuzu, duman, volkanik eş gibi doğal emisyonları, doğal aerosolleri tanımlayabildiğimiz gibi endüstriyel emisyonlar ya da araba egzozları, ev bacaları gibi fosil yakıt yanmaları sonucu atmosfere bırakılan insan kaynaklı antropojenik emisyonlar da tanımlanıyor. Burada güzel bir animasyon var. Bu simülasyonu sizlerle paylaşmak istedim. Burada 2017 yılı Ağustos ayından Ekim ayına kadar hem sahradan kalkan kahverengi renkli çöl tozlarını görebiliyorsunuz. Yine mavi renkli deniz tuzu ve özellikle Amerika kıtasına baktığımız zaman da ciddi orman yangınlarından açığa çıkan emisyonları ya da dumanı tanımlayabiliyoruz. Emel Hanım da yine biraz önce bahsetti. Hakikaten küresel bir problem ve binlerce kilometre uzağa taşınabiliyor. Özellikle Sahra tek başına dünyadaki bütün toz emisyonlarını yaklaşık olarak yarısını atıyor. Toz emisyonu dediğimiz zaman da atmosferdeki aerosollerin, özellikle doğal aerosollerin çok büyük bir bölümünü tozlar ve deniz tuzu oluşturuyor. O nedenle kritik. 10 mikron gibi daha büyük parçacıklar kaynak alanı yakınlarında çökerken 1 mikrona varan, 2,5 mikrona varan daha küçükler binlerce kilometre taşınıyor. Zaten literatüre baktığınız zaman Amazon ormanlarının ve okyanusların besin kaynağı olarak da sahra tozları gösteriliyor. Biraz önce de söylediğim gibi dünya atmosferine her yıl yaklaşık 2 milyar ton çöl tozları atılıyor. Bunun yaklaşık olarak 1 milyar tonu tek başına Sahra tarafından atmosfere bırakılıyor. Eğer Orta Doğu ve İran çöllerinde işin içine katarsanız 3'te 2'si diyebileceğimiz bir miktarı Türkiye'nin etrafından atmosfere salınıyor. Biz şimdi bu tanımladığımız aerosollerin analizlerine geçersek biz bu analizlerde neyi kullandık? NASA'nın Aqua uydusu üzerindeki MODIS aygıtından elde edilen aerosol optik derinliği verilerini, ayrıca ECMP-CAMS modelinin Kopernik programı kapsamında geliştirilmiş olan CAMS modelinin verilerini kullandık. Aerosol optik derinliği verisi birimsel bir parametre. Yaklaşık 0 ile 1 arasında gidip gelen, işte 0,3'ün üstünde ise daha çok çöl tozlarından bahsedildi. Ama biraz önce Konya örneğinde yaşadığımız gibi ya da burada işte Suudi Arabistan, Riyad'da yaşanan 2009 yılındaki bir toz fırtınasını görüyorsunuz. Burada değerlerin 3'e 4'e kadar çıktığı uydu ölçümlerinde ve yer ölçümlerinde tespit edilmiş durumda. Birimsiz bir parametre dediğim gibi. Dünya geneline baktığımız zaman küresel olarak zaten toz kaynak alanları büyük ölçekte Afrika'da var, Orta Doğu'da var ve Güneydoğu Asya'da var. Bir de yukarıda göreceksiniz Aral Gölü, artık Aral Çölü dememiz gerekiyor muhtemelen. İnanılmaz bir derecede yoğun atmosfere emisyon bırakıyor. Kopernik programı kapsamında geliştirilen CAMS modelinin datasına baktığımız zaman bir önceki uydu verisine benzer bir şemayla, durumla karşılaşıyoruz. Şimdi bunların yıl yıl değişimlerini incelediğimiz zaman, daha doğrusu zaman zaman işte uluslararası toplantılarda bu dile getiriliyor, kamuoyuna yansıyor. İşte iklim değişikliğiyle birlikte çöl tozları çok arttı, işte her taraf çöl olacak gibi argümanları görüyorsunuz. Zaman zaman komşu ülkelerden bizi suçlayan argümanlar, işte aşırı baraj yapımı sonucu alt havzalarda kuruma kaynaklı da tozların arttığına dair argümanlar oluyor ama tam da o şekilde değil. Çünkü dünya ölçeğinde baktığınız zaman kesik çizgiyle gördüğümüz dünya çok önemli bir atmosferdeki tozlarda değişiklik yok. Açık maviyle gördüğümüz Avrupa'da, yani mouse gözüküyor mu bilmiyorum. Hatta yine sabah Ülke Hoca'nın sunumunda vardı. Ciddi demeyelim, hafif bir azalma trendi ama düzenli bir azalma trendi görüyorsunuz. Koyu mavi Türkiye, çok önemli bir değişiklik yok ama artış ve azalan dönemler var. Sıkıntılı bölgeler Afrika, Orta Doğu ve Güney Asya. Burada zaman zaman zaten değerler yüksek, AOD değerleri, yani kum toz fırtınalarının yoğun olduğu bölgeler. Bazı yıllarda ciddi artışlar ve bazı yıllarda ciddi azalmalar var. Bizim tespit ettiğimiz 2008-2012 yılları arasında bütün bölgelerde aşağı yukarı bir uzun yıllar ortalamasının üzerinde seyir görüyoruz. 2018 yılında tekrar pik yaptığını görüyoruz. Bu grafikte yok tabii. 2022 yılının içinde bulunduğumuz yılın ilkbahar döneminde yine bizim bölgemizde başka bir pik daha gördük. Bunun aylık dağılımına baktığımız zaman yine literatürde de benzer şekilde bizim bulgularımıza destekleyen değerleri görebiliyoruz. Özellikle Akdeniz Havzası'nda Sahra'nın ilkbahar mevsiminde, ilkbahar aylarında Akdeniz'in doğusuna, sonbahar aylarında da batısında daha etkili olduğu, daha fazla toz gönderdiği gözüküyor. O nedenle mavi çizgiyle alttan işte 3. çizgiye baktığınız zaman Türkiye Mayıs ayında pik değerlere ulaşıyor. İlkbaharda yüksek, yazın yine bu kurak dönemlerde değerler yüksek seyrediyor. Fakat kış dönemine girdiğimiz zaman yani Mart döneminde başlayan tozlu dönem diye tanımlayabileceğimiz Eylül sonu itibariyle neredeyse Türkiye açısından bitiyor. Konya örneği başka bir örnek. O bizim kendi içimizden kaynaklanan emisyonlardan. Yani bunu zaman zaman şeyde de Güneydoğu Anadolu bölgesinde de görebiliyoruz. Birkaç sene önce Polatlı'da çok ciddi bir benzer uluslararası literatüre Arapça habub diye geçen olayı yaşadık. Şeyde biraz daha durum farklı. Özellikle Orta Doğu'da, Afrika'dan farklı olarak, Sahra'dan farklı olarak, Orta Doğu'da ve Güneydoğu Asya'da baktığınız zaman pik değerleri hep Temmuz'da görüyoruz. Bunun sebebi ne olabilir diye düşünün. Literatür karıştırdık birazcık. Çok somut verilerle objektif sonuçlar elde etmemekle birlikte musonların etkisini görüyoruz. Musonlar Temmuz ayı en baskın olmak üzere yaz aylarında kuvvetli güney batılı şekilde Orta Doğu'ya geliyor ve Asya'ya geliyor. Güneyli rüzgarlarda kurak alanlardan tozları kaldırıp atmosferdeki konsantrasyonu artırıyor. Kış aylarında ise rüzgarlar, muson rüzgarları kuzeyli bu sefer. Yani muson sistemindeki rüzgarlar kuzeyli. O nedenle çok fazla toz kalkışına, atmosfere toz karışmasına sebep olmuyor. Tabii bu sunumu yaparken Meteoroloji Genel Müdürlüğü'nün çalışmalarından da çok kısa bahsetmek istiyorum. Bizim hem Batı Asya bölgesi hem de kendi ülkemiz için ürettiğimiz toz tahminleri hem yüzey konsantrasyonu olarak hem de aerosol optik derinliği olarak internet sitemimizde operasyon olarak günlük yayınlanmakta. Yine iller için toz uyarı sistemi dediğimiz, buraya koymadığımız günlük ortalamaların olduğu, kullanıcılar için daha yol gösterici, daha kolay anlaşılır bir ürünümüz daha var. Yine uydudan düzenli olarak UNETSAT'ın MSG uydusundan aldığımız toz ürünü biraz önce Emel Hanım göstermişti Konya'daki olayı. Bunu da saatlik olarak internet sitemizde yayınlıyoruz. Buradan da takip edebilirsiniz. Bugün 06 Z yani sabah 9 lokal saate karşılık gelen ürün. Bu da bugün 12 Z yani şu anda 15. Bugüne şu anda bulunduğumuz duruma karşılık gelen tahminimiz. Peki tahminlerin tutarlılığı ne derseniz, bunu yine hem APO hem de Terra üzerindeki MODIS cihazının AOD ölçümleriyle verifiye ettiğimizde, değerlendirdiğimizde, verifikasyon demeyelim ona, aslında oldukça yüksek bir korelasyon, ilişki olduğunu görüyoruz tahmin edilen değerlerle. Ölçülen değerler arasında çok iyi bir ilişki var. Bunun sebebi de zaten Kopernik programı kapsamında üretilen kum ve toz fırtınaları ya da toz taşının tahminlerinin modelin uydu verisiyle asimile edilmesi olduğunu söyleyebiliriz. İşte Türkiye için 2020 yılında 0.75, bunun 0.80, 90, 95'lere kadar çıktığını gördük. Özellikle toz döneminde biraz daha başarısı artıyor modelin. Burada yansıya koymadım ama bir eksikliği de şu. Küresel ölçekte başarılı olan model, biraz önce Konya örneğinde olduğu gibi Türkiye'nin kendi içinden kaynaklanan toz emisyonlarını çok fazla yakalayamıyor. Daha büyük alanlar için geliştirilmiş, işte Sahra için, Orta Doğu'daki çöller için geliştirilmiş bir model. Maalesef bizim iç bölgelerden taşınımları görmüyor. Bir de son olarak dile getirmek istediğim bir konu var. Aerosoller ya da toz niye bu kadar önemli? Burada dünyanın son yarım milyon yıldaki atmosferin analizini görüyorsunuz. Buzul örneklerinden yapılan analizlerde elde edilen sonuçlar. Bunu da NASA kayıtlarından, NOAA kayıtlarından özür dilerim aldım. NOAA kayıtlarına baktığınız zaman dünyamız işte bundan işte yaklaşık 20.000 sene önce, 50.000 sene önce ya da ne bileyim 150.000 sene önce değişik dönemlerde hem buzul çağlarını yaşamış hem sıcak dönemleri yaşamış. Bu sıcak ve soğuk dönemlere karşılık gelen karbondioksit konsantrasyonları, yani belirleyici sera gazı konsantrasyonuna baktığınız zaman soğuk dönemlerde karbondioksitin minimuma düştüğünü, sıcak dönemlerde ise çok yükseldiğini görüyoruz. Fakat dikkat etmemiz gereken konu, dünya son yarım milyon yıldır 300 mikrogram bölü metreküp değerini hiç aşmamış. 300 ppm değerini hiç aşmamış ama şu anda 420'ler civarında, 400'ü geçmiş durumda. O nedenle bu insan kaynaklı literatürde yine geçen iklim değişikliğinin, yani dünyanın kendi iklim değişkenliğinden farklı olarak insan kaynaklı etkisinden kaynaklı iklim değişikliğinin etkileri konusunda daha farklı senaryolar dile getiriliyor. En alt grafikte ise kutuplardaki toz konsantrasyonunu görüyoruz. İlginçtir. Dünya ne zaman buzul çağına girdiyse kutuplarda inanılmaz miktarda yüksek toz konsantrasyonları rastlıyoruz. Biz şunu da biliyoruz ki aerosoller toz başta olmak üzere. Güneş ışığını yansıtma etkisinden dolayı aslında dünyaya soğutucu anlamda bir katkı sağlıyor. Yani iklim değişikliği ya da küresel ısınma diye tanımlanan olay karşısında dünyanın kendisini bir nevi savunma mekanizması olarak tanımlayabiliriz bunu. Bir sonraki slaytta çok daha net şöyle bir tespit var. Sabah Ülke hocamız demişti. İşte İngiltere'de, Avrupa'da ve Amerika'da PM2,5'un yavaşça azaldığını belirtmişti. Biraz önceki grafikte ben de söylemiştim. Avrupa'da eğer bakarsanız Kuzey Amerika alanını seçip Moody's datasından benzer durum orada da görebilirsiniz. Evet, bir azalma var. Hatta bu azalmayı IPCC 2021 raporunda da belirtmiş ve bu raporda diyor ki azalan aerosol konsantrasyonları Avrupa üzerindeki kısa dalgalı radyasyon trendine pozitif etki edeceği için ısınma yönünde bir katkı sağlayacaktır gibi bir yorum yapıyor. Yani bizim aslında hava kalitesini iyileştirdiğimiz süreçte bu sefer de bize iklim değişikliğinin işte bir bileşeni olan küresel ısınma şeklinde geri dönebileceğine dair ipuçlarını bu paragrafta görebiliyoruz. Aşağıda da 10'ar yıllık 3 tane grafik konulmuş. İşte 96'da baktığınız zaman çok daha fazla atmosferde aerosol varken özellikle Avrupa atmosferinde tabii alınan bu kafe direktifiyle birlikte Avrupa Birliği'nin hava kalitesi iyileştirmeleri sonucunda Avrupa atmosferindeki aerosollerin azaldığını görüyoruz. Ben çok teşekkür ediyorum sabırla dinlediğiniz için.
Thank you very much, Cihan Dündar. Is there any questions about dust, sand, about these subjects, etc.?
Salondan soru var.
Please.
Sayın Dündar, çok teşekkürler.
Daha yakın.
Için çok
Deniz Hocam daha yakın.
bir çalışma oldu. Şunu kaçırdın mı yoksa bu çalışmaya sonradan mı ekleyeceksiniz? Güneşten gelen radyasyonun, kısa dalga boylu radyasyonun şu anda bir etkisi var mı? Partiküler madde o kadar fazla mı? Ne durumda güneşten gelen radyasyonun ilişkisini açıkladınız mı? Tam onu kaçırdım ben galiba. Sizin verilerinize göre yani.
Sayın Hocam, salon az duyuluyor ama anladığım kadarıyla güneşten gelen kısa dalgalı radyasyonun miktarında bir değişiklik oldu mu, bir artış oldu mu gibi algıladım. Eğer doğru duyduysam, hani bizim çalışmamızın asıl konusu değil o. Hatta ben o slaydı 1 saat önce ekledim ilk hocayı dinledikten sonra. Bu konuya da tekrar bir bakmak lazım. Yani Avrupa'da kısa dalgalı radyasyonun ya da güneş radyasyonun miktarının Avrupa coğrafyasında artıp artmadığı konusunda bilgimiz yok.
Teşekkür ederim.
Salonun başka sorusu yok hocam.
Thank you very much, Cihan. Now we continue our new studies, investigation of dispersion models and possible health effects on air pollution emitted from an industrial plant, prepared by Ömer Mert Bayraktar, Atilla Mutlu.
Hello, everyone.
Hello, welcome.
Hello.
Now the screen, the microphone is for you.
Okay, thank you so much, Professor Toros. My name is Atilla Mutlu from Balıkesir University, and this study, let me share with you. Okay, this study, actually one of my graduate students research, and today he's not able to present this his study, so I'm the one who's presenting for all attendees in this valuable symposium. Today we'll be discussing different dispersion models, and we will compare based on the airborne particle meters PM10, and also the heavy metal analysis and health effects from industrial plant. As you may know, the air pollution is still one of the major industrial environmental problems in our human society. So the latest technology parallel to improve developing the computerized calculations and the similar similar programs or algorithms, the dispersion models and forecasting now is more important to the way understand their behavior and any possible health effects to the human society. So therefore, we try to design this study. Here's the meteorological models and air quality models, and most of you are familiar with these models, and we use the HARP models for the health to figure out the health effects. So this is the flow charts, the main basic steps of our study. What we did here, actually, we continue the local meteorological data. This is the step A. And step B, we also collect the data from WRF. This is the...
Attila,
yes.
Is there any presentation? You can share if you want.
Actually, I did. Can you see the presentation? All my slides?
No, I haven't.
Okay, let me start again. I'm sorry. Here. Okay. How about now, Professor Toros?
Okay, continue,
okay.
Please.
So let me comment what I said here. Okay. Okay, let me make it bigger. Okay. I just talk about, I said the air pollution is one of the major environmental problems. This is the meteorological models, air quality dispersion models, and health models. We used WRF as a meteorological models or forecasting models, air quality dispersion models, AirMod, ATMOS, and ISC3. And health models, we used HARP for this study. So this is our method, the basic steps. And in steps A, we collect the local meteorological data from local stations. And we do the same thing in the B. We collect the satellite data from WRF and for AirMed and for WRF. And we run the three AirMod, ATMOS, and ISC3 air quality models. And we did some statistical analysis. And we also used the HARP model to figure out any health effects, any risk in terms of cancer, acute or chronic risk for the human from the 70 years time spans. So this is a study area in Balıkesir. There's airport, here's local meteorological station at the airport. Here's a cement plant, and approximately 1 kilometer of the east of the cement plant, we have the city hospital. We have 2 air quality monitoring stations, A and B, and this area we call the downtown, basically downtown. In the cement plant, we have major 4 stacks with their PM10 emissions here. We have also a transportation line in red line here. We have also unloading area here. And we have also the storage area of the final product of cement here. So this is a heavy metal emission inventories, especially the stack 1 has the more heavy metal emissions, the arsenic and chromium, lead, vanadium are the highest values. So as I stated before, what we did, we collect the local local meteorological data. So we have 2 different data, surface data and upper air data. Surface data we collected from the local air station, which is Balıkesir Airport, 17150. And upper air, the radius on the data, we gather from the Kartal, Istanbul Kartal region, 17064. So we employ both data for AirMet as a surface data and the upper air data. We also use try to gather the meteorological data from WRF, and we created our grids. Outer grids, out domain was 2000 by 2000 kilometers and 30 by 30 kilometers grid. And we also choose the inner domain, which is 400 by 400 kilometers area and 10 by 10 kilometers grid. Okay, here's, I'd like to share our domains in here, region, outer and inner. So this is the main model flow charts. We collect the local station data, we collect the WRF data.
Dear Attila,
AirMet.
sorry.
Yes.
Dear Attila, sorry, please, you can change presentations. Slide is not changing.
Slide is not changing, okay.
Yes, yes, yes, it is. Okay, how about now, Professor Toros? Is it okay? Okay, okay,
all right. I guess there's a time limitation, something. Okay, so this is the basic, the major model flow charts. We used meteorological data. From those meteorological data, we use AirMet and WRF, basically. AirMet goes to ADMS, air mode, and ISC, the air quality models. WRF, we cannot send all the WRF results through the air quality models. We need the interface model, which is called MMI5. It's the basically compiler to send through those air quality models. So after we prepared all the WRF data, so we need to use MMI5 data to run those air quality models. And all the results we combined with the health risk model, which is hard data. This is our study concept. So this is, I just mentioned meteorological data, surface data, upper air and on-site data goes to AirMet. From AirMet, we have two separate data, surface and profiles data. AirMet also includes some physical properties, which is albedo, Bowen ratio, and roughness, surface roughness. So with this, all the AirMet preparation we can employ through the air quality models. This is the WRF here. And we explained all the details, how we gathered the data and what was the time scales and time spans. And you may find in our full paper for this symposium. Also, we run some MMI5, as I mentioned before, mesoscale model interface program to compile the WRF and similar data through the air quality analysis. Okay, so we have basically ISC3, air mode, and ADMS data. ISC3, the submodel of air mode right now is air mode is the wallet is satisfied for all air quality analysis, and ADMS, IC3 and air mode is the United States based models, and ADMS is British based models. Here's the flow chart of air mode. And what we gather here, based on the industrial air pollution regulations, we set up our 4 kilometers diameter grids. And we used both to keep the consistency. We used 2019 data, and we combined all site data industrial data, meteorological data, and everything we used in 2019. And here's the results, the initial major results for daily results. Local, the air mode here, local, we run the air mode using the local meteorological data and also WRF data. And we can see the difference here and daily data, and also ATMOS here and ISC3 here. And basically, the in terms of the highest value, we didn't notice any big difference. So this is the annual and 1 year data in 2019. Air mode here, local data, and air mode used WRF data. ATMOS used local data, local meteorological data, and coupled with WRF data, and also ISC3. Okay, here's the, let me put side away my name. Okay, what we did here, we put everything, air quality monitoring stations A and B, and what our models estimate. So we put together and try to understand how the readings and estimation close to each other. So we prepared a Spearman correlation because our data was not normally distributed. So that's why, based on the correlation data, here is in the green numbers, what we learn here, WRF with air mode data for AQMS A has the highest correlation, and also for the B, the second AQMS air quality monitoring station has also the highest correlations values. So therefore, we can understand that air mode, both air quality monitoring stations, air mode with WRF data had the reliable data. And we also run the HARP model. HARP model is basically the air toxicity analyzed model. So it has three components. One is the emissions inventory model. The other one is air dispersion modeling and risk assessment tool. And the last part is a risk assessment standalone tool. And here's the flow chart for the HARP. So let me talk about the little baseline step, the basic setup here. We used the PM10 and heavy metal, and also we use inhalation scenarios for 70 years time span. So basically the program, the maximum time span for the lifetime is 70 years. So we use 70 years for cancer, chronic, and acute possible disease. So what we have here, basically the minimum limit means any possible cancer risk from the air pollutants or heavy metal concentrations. Risk value is 1 in a million person. For Balıkesir case, we got the highest number, 6 for WRF air mode, 6 person in a million, and air mode, which is local meteorological data with air mode, we estimated 7. So the mean is over little about 1 person, 107 or 0.99. So we can say that around 1 is about the limit. But the highest value, highest estimation, 6 and 7. So this is the exceed the USCPA limitations. For this is the also distributions for the health risk for the cancer. Also chronic disease. Actually, the chronic disease didn't exceed the US EPA limit, and also is also the dispersion of the chronic disease from the same area. And acute disease, we didn't notice any exceedance of the EPA limits. So those are the major findings for our studies. So what we learned from this study, the local data from the local meteorological stations, we always challenge with the calm air, which is showing the 0 meters per second wind speed, and almost 30% of the data were missing. For satellite data, we gathered more complete data and more reliable data, and when we used together with the satellite data with the air quality data, we get the better results so far. So in terms of air quality models, the short time, hourly timeline was found that WRF ATMOS has more reliable data. For peak daily correlations was found WRF for air mode model. In terms of meteorological models, we prefer to use WRF model, which has more comprehensive atmospheric physics options. So this is one of our priorities, using the WRF data for the next future air quality studies. And also the health risk analysis using the HARP. Cancer risk exceeds the US EPA limits. Acute and chronic, both those risks were under the limit of the US EPA. Thank you for listening to me. Is there any questions? I'll be more than happy to help answer.
Dear Attila, thank you very much. We have no more time for asking questions. Maybe they can ask you via email.
Sure,
now,
anytime.
We can continue other presentation. The subject is impact of the pandemic on air quality, urban and rural case study prepared by Furkan Ali Küçük and Ceyhan Kahya. I think
Hello everyone. Can you hear me?
Welcome Furkan. We are ready and we are hearing you.
Okay,
you
thank
can
you.
share your presentation and continue, please.
Yeah, can you see me? There's a problem. There's a black line, but I don't know what happens. I share my screen. So
please, you can share your screen. Yes, now we can see your presentation.
Yeah, okay. Which one? Yep. You see presentation outline? Yes, okay.
Yes, outline. Okay.
Hello, everyone. My name is Furkan Ali Küçük. I am a PhD student at Istanbul Technical University, Atmospheric Sciences. Also, I work as a researcher at TÜBİTAK Polar Research Institute. Now I am working at Gebze because of I couldn't hear there. I'm sorry for that. Today I would like to talk about impact of the pandemic periods on air quality, urban and rural case study. This is my presentation outline: introduction, study area, our material and methods. Also, we have two analysis methods, regression analysis and continuous variable analysis. After that, I show our conclusion. So, introduction. In this study, a comparative analysis of PM10, SO2 and NO2 data for Kağıthane and Arnavutköy during the pandemic period in April and May 2020, 2021 and 22. As you know, COVID is a highly contagious disease first identified in December 2019 in Wuhan, China. The first case of the figure 2 shows us COVID figures of the Turkey between March 10th and May. Also, with the nationwide quarantine, almost all industrial activities, going out in the streets, and public transformation were banned. This is a study area location figure. Sorry. Yeah. This is a study area, locations of the study area and air quality stations. We chose Kağıthane and Arnavutköy. Also, this study focused on two discrete. We use ECMWF model data, and together Istanbul Metropolitan Municipality Environmental Protection data. Due to high acceleration in population growth brought by rapid industrialization, economic problems, uncontrolled migration, and unplanned urbanization, its for negative effects on society continue to increase day by day. Because of that, we select Kağıthane and Arnavutköy. Also, we can say that Arnavutköy as a rural district, also Kağıthane as a city center or urban area. So, analyzers the data measured at air quality stations include the period from April and May 2020, 2021, 2022. First of all, regression analysis was performed to reveal the relationship between the data. Secondly, we use continuous variate transform. Also, regression analysis. This figure shows us distribution and regression analysis of PM10, PM2.5, SO2 and NO2 for the discrete of Kağıthane for these years. This one is for 2020. This one is 2021 and also 22. It was observed that the pollution measured in Istanbul, Kağıthane, and discrete in April and May. So, considering the regression line and coefficient between PM, yes, I don't know, you see PM10, this is PM10, this is PM 2.5 and SO2. Considering the regression line and confusing between PM10 and PM 2.5, there is it is seen that there's an important linear relationship. Also, the regression line and coefficient between SO2 measurement values and PM 2.5 and PM10. There is no significant relationship for 2020. Also, the regression line, also considering the values measuring in Kağıthane discrete, the lowest PM 2.5 and PM10 values for 2020 were measured in the first week of May, while SO2 values were measured in the last week of May. So we can see that. It is seen that there is a relatively linear relationship between also NO2, there is the NO2 and PM, where is NO2? Yeah, NO2 and PM10 and NO2 and SO2, there is a significant relationship. Okay, the figure shows us the distribution and regression analysis, the particular methods for the Arnavutköy and these years. Considering regression line and coefficient evaluated between the scope of the 2021 measurements. There's a 65% linear relationship. You can see that there's a similar like Arnavutköy and Kağıthane district. There's a similar in NO2 and PM 2.5. There's no difference. And also the figure shows us SO2 and NO2 wavelet analysis and PM10 data for April and May these years. The SO2 and NO2 wavelet analysis that looking at this is I show you this is the this part is 2020, this part is 2001, and this part is 2002. Also here. So looking at May 2021 and April-May period of the 2022, a significant positive trend is observed between PM10 and NO2. Also PM10 and SO2. There is a significant medium large scale. So this figure shows us Kağıthane wavelet analysis. The SO2 and NO2 wavelet analysis of PM10 data for the April and May. So looking at the distribution between PM10 and NO2, there is a positive trend is seen in the middle scale. This is the middle scale. Red is one positive scale. Blue is one negative trend. I forgot to say that. Sorry. So, a conclusion: it is seen that the COVID pandemic has improved Istanbul's air quality in the short term and has made a significant contribution to reduce carbon emission. Also, it is seen that the linear relations of PM10, PM2.5, SO2 and NO2 data measured in Arnavutköy district by years are higher than in Kağıthane district. Also, it was observed that the change in the rural area among atmospheric pollutants was lower between the beginning and end of the pandemic period. We can say that. Also, thanks to this study, it has been shown how pollutant increase with each passing day with the return of the normal life in the time intervals shown for the different periods of pandemic process and how they tend to be in which types of the region with each others. So thank you for your attention. Okay, I close my.
Dear Furkan, thank you very much for your nice presentation, your studies. Is there any questions we have time to ask?
Okay.
I hope the impact of pandemic situation may be helpful or not for air quality, but we don't like pandemic conditions. I hope we can't see again these situations. Thank you very much for nice studies.
Thank you.
Now the subject is sensitivity of high-speed back trajectory clustering to meteorological inputs, prepared by Deniz Genç, Kokgöz, Firdevs, Doğrusever. I hope they are ready.
Yes, we are here.
Thank you very much for preparing your nice studies. Now the screen for you. You can share and microphone for you.
Thank you very much, Dr. Toros.
The title of our study is Sensitivity of High-Split Back Trajectory Clustering to Meteorological Inputs. This study is actually, we prepared this study with my graduate student Firdevs Doğrusever. And today I am presenting this study. I want to start with a definition of trajectory. I am sure most of you already familiar what is trajectory. In air pollution studies, we usually use trajectories to describe the movement of air masses. And actually, trajectories are just an estimate. There are many uncertainties in trajectories because to calculate the air path of air masses, you should provide meteorological data in the upper atmosphere. And these meteorological input data actually are product of meteorological models. So there are many uncertainties. But trajectories are very important for air pollution studies because we need to know where is the source of air pollution, especially in long-range transport studies. We use back trajectories that describes the history of air mass. Which locations did this air mass pass before reaching our station? Which pollutants they captured? Of course, we cannot define which pollutants by trajectories, but we just know which locations did these air masses passes through before reaching to our station. Okay, there are many trajectory models that can be used, but among them, high-split, hybrid, single particle Lagrangian integrated trajectory model is the common model that most of the air pollution researchers use because it is available. You can use it on web and it is free. Therefore, most people prefer to use high-split model. I already told that to run the high-split model, trajectory model, you should provide meteorological data. For high-split model, there are 4 different meteorological data that can be available. But each of these meteorological data has different horizontal, temporal, and vertical resolutions. So, of course, their product will be different. In air pollution studies, actually, we are not dealing with single trajectories. We deal with many trajectories, hundreds, thousands trajectories, because our aim is to see what is the our aim is to determine the synoptic scale air movements, and with these air movements we want to see the relation between high pollution concentrations. When we have high pollution concentration, air mass, in which direction did air mass comes? In which regions it passed through? So we use many trajectories in our studies. And we call it as trajectory analysis. There are 3 different trajectory analysis methods that we usually prefer to use. These are potential source contribution function, concentration weighted trajectory, and trajectory clustering methods. I want to give some examples from our previous study. we have a station in northwestern Turkey, and we have aerosol measurements, and we measured sulfide, nitrite, and many elements. And we calculate, we simulate trajectories, and then we apply potential source contribution function, and we determine the potential source regions. For example, in this figure, the potential source regions for sulfate are indicated with orange and red colors. When we look at the point sources, actual sources in these regions, we saw that, yes, there are many large point sulfur sources in Ukraine and Russia. That our study shows these regions at hotspots. We also, another trajectory analysis method that we use trajectories is cluster analysis. Yeah, I mentioned that we are not using single trajectories, we are using large groups of trajectories. Here, I think there are more than 2,000 trajectories here. We classify them into similar direction and speed, so that each group represents different transport direction. And then we again relate these clusters, these air movements, with pollutant concentrations. There is an example again from our previous study. Here we relate cluster centers with air pollutants. Here, soluble potassium concentration. You see average soluble potassium concentration in each cluster center. Here, cluster 5 has significantly higher soluble potassium concentration. When we look at cluster 5, we saw that it indicates Ukraine and Russia. And we know that soluble potassium is a marker for biomass burning. Therefore, we thought that this indicates that relation between forest fires. When we investigate the dates that has higher soluble potassium concentration, we downloaded forest fire maps for these dates, and then we check back trajectories on these days. And we saw that when there are forest fires on Ukraine and Russia, most of the back trajectories were from Russia and Ukraine. So the forest fires, the impact of forest fires from the Russia and Ukraine reaches to the northwestern Turkey. These are just examples that how we use back trajectories in air pollution studies. Yes, meteorological data is very important, and there are different meteorological data that can be used with high-split model, but there are also different input parameters that a user should choose while running the high-split model. A user should choose vertical motion option, and a user should choose arriving height of the trajectories and arriving time. It is starting location. There are many input parameters that a user should choose to run the high split, and all of these input differences create different trajectories. To show the
importance of input parameters, for the same day, we simulate back trajectories using different meteorological archive. For example, in the first figure, you see that air masses travel from Libya to Mediterranean to reach our station. When we use another meteorological data, GDAS-1 meteorological data, we saw that air masses originate from Aegean Sea and it travels through Turkey and then reach to our station. Totally different. Same day, but using different meteorological archives. What about the vertical transport velocity? If we use different vertical transport velocities, but using the same meteorological archive here, isentropic trajectories are simulated. Again, it originates from Aegean Sea, travels over Turkey, and then reach our station. If we use the kinematic model, we saw that, okay, it again started from Aegean Sea, but moves short time in Turkey and reached to our station. So, meteorological archive and vertical transport velocity methods really make differences. When we look at the air pollution studies in Turkey, we saw that most of the studies use high split model, and they usually choose reanalysis and GDAS-1 meteorological archive. And for vertical transport methods, they use either isentropic or kinematic trajectories methods. It was interesting to see that in some studies, which meteorological archive is used or which vertical transport method is used is not reported. It was very interesting because these impulse data really important, and they can create different results. So in our study, we want to investigate the sensitivity of meteorological data and vertical velocity methods on simulated back trajectories. For this sensitivity analysis, we use 4 different data. For meteorological archive, we use reanalysis meteorological archive 1 here, and 2 represents the second meteorological archive, GDAS-1 meteorological archive, and we use 2 different vertical velocity methods. A represents the isentropic trajectories and B represents the kinematic trajectories. For sensitivity analysis, we create 4 different scenarios. The orange one is conducted to determine the sensitivity to the velocity method, and the green one is selected to determine the sensitivity to meteorological archive, and the blue one is chosen to determine the sensitivity to both meteorological archive and velocity method. We use some sensitivity parameters to calculate how actually diverge these trajectories from each other, from horizontal and from vertical. These sensitivity parameters are absolute horizontal transport deviation, relative horizontal transport deviation, and absolute vertical transport deviation. I will not go into detail of these equations, and I want to get the results. Okay, please
give your attention this relative horizontal transport deviation. It gives the result as percentage. It will make more sense. Okay, when we look at the orange one, the comparison to the velocity method, we saw that when we use the reanalysis methodological archive, actually it is not so sensitive to velocity method. But when we use GDAS1 methodological archive, we saw that velocity method is really matters. The sensitivity is more than 40%. And both isentropic and kinematic trajectories are found to be sensitive to the methodological archive. They are nearly has sensitivities around 40%. So our sensitivity analysis show that reanalysis is less sensitive to vertical transport method, while GDAS1 is the most sensitive to vertical transport method, and isentropic and kinematic trajectories are both sensitive to methodological archive. And we saw that here, individual trajectories are sensitive to both methodological archive and vertical transport method. Actually, we also investigate time evolution of these sensitivities.
Dear Dennis,
yeah,
time is finished. Please, you
really?
Can summarize your studies. Yes.
Okay, I am sorry. Okay, here we saw that when we keep the trajectories length longer, mean time longer. If we simulate 5-day trajectories, our errors increases. But if we use shorter trajectories, it means that 1 day, 2 day, accuracy is higher. Okay, I can say that individual trajectories are more sensitive to input parameters, but if we use trajectory analysis, I mean, if we use large trajectory data sets, the sensitivities are decreasing, and we can get, or let's say we can increase the accuracy. Thank you very much for your attention, and we will be happy to hear your questions, comments, or any contribution.
Dear Dennis, the subject is very complex. High-speed back trajectories and air pollution clustering. The subject is very complex. I hope you can continue this kind of studies. We need more episodes, periods, studies, etc. To analyze and to find results. Sometimes very difficult. Thank you very much for nice studies. Now we have time to any questions they can ask you via email.
Yeah, we will be very happy.
Okay, thank you very much. Now the subject is impact of COVID-19 pandemic on the air quality in Turkey. The subject again about pandemic conditions. Prepared by Samet Öztürk. Samet Öztürk is ready?
Yes, I'm ready. I wanted to share my screen, but it says the previous user needs to stop.
Please, Dennis, you can stop sharing the screen.
All right. Hello, everyone. My name is Samet Öztürk. I work as an assistant professor at Bursa Technical University in Environmental Engineering Department. I'll talk about the impact of COVID-19 on the air quality in Turkey. As you all know, the COVID-19 started in 2019, December 31st. On March 11, 2020, the WHO, World Health Organization, declared that it's a pandemic. and the COVID since then led to lots of challenges in countries around the world in terms of the social, economic, and obviously the health aspects. However, some researchers found that the pandemic improved environmental quality in some aspects, and the air is one of these aspects. Here you can see the literature review. In some studies around the world, researchers investigated the impact of COVID-19 restrictions on the air quality. For example, Hu et al., they looked at the 20 largest populated cities in the world, and they found that the NO2 levels are significantly decreased due to the pandemic restrictions. In another study, the 12 cities were investigated, and PM10 and PM2.5 levels were found to be significantly reduced during the restrictions. In another study, 50 most populated countries are investigated in terms of PM2.5 variations, and they found again a significant decrease in the level of PM2.5. And similarly, there are lots of studies in specific parts of the world in the literature. However, only a few studies in the literature investigated the impact of COVID-19 pandemic restrictions on the air quality for Turkey. For example, Aydın et al. Investigated in PM2.5 level change during the pandemic, and they found that it's decreased significantly. And Şahin investigated a correlation between SO2 content and the number of COVID-19 cases, and they found that there's a correlation. And the motivation actually for this study is that investigating the high populated cities and lowest populated cities air quality during the pandemic and before the pandemic, and make a comparison between those years. As you're familiar, there were several restrictions during the COVID-19 period in Turkey. Actually, COVID-19 is still going on, but I mean the restriction times. There were some limited mobility. For example, people were forbidden to go out at some specific time of the days. There were total lockdowns in some period, like 21 days or so. And during another example of COVID-19 restriction was a remote work and remote education periods. So the objective of this study is to investigate the impact of the air quality intensities with 6 air pollutants. What are these 6 air pollutants? They are listed here: nitrogen dioxide, sulfur dioxide, carbon monoxide, ozone, and particulate matters, specifically PM10 and PM2.5. And data come from the Turkish Ministry of Environment, Urbanization and Climate Change. Maybe you may know that there are some stations in all cities of Turkey collecting data of the air quality. Here in this table, you can see that the parameters of corresponding city, actually, unfortunately, not all of the air pollutant parameters can be collected in all cities. Basically, for example, in Tunceli, which is one of the least populated city in Turkey, there is only one parameter collecting station, namely SO2. In terms of the high populated cities, Ankara, Antalya, Bursa, Istanbul, and Izmir, in Istanbul, both sites are included in this study as European side and Asian side. So the methodology applies the periods specifically between 11th of March and 31st of May. Why I chose this? Because the restrictions were applied in 2020 in between these in between these dates. So the same exact periods were taken for 2017, 2018, 2019, and 2020 to compare the same with the same exact time of the years. And the statistical method to compare the air pollutant values is one-way ANOVA, and post-hoc tests are applied as Taki tests to compare pairwise as well. Let me talk about some results now. Per carbon monoxide, there were no data for the least populated cities. So we can only compare the highest populated cities for carbon monoxide. You can see the box plots here, but the statistical in terms of the statistical significance, only carbon monoxide levels at Bursa and Izmir in 2020 were found to be statistically significant. For Bursa, the significance occurred between 18 and 20 and 19 and 20, and it was an increase of CO2 between 18 and 20 and 19 and 20. For Izmir, there was a statistically significant decrease between 17 and 20 and 18 and 20, whereas there was a statistically significant increase between 19 and 20 for Izmir. For nitrogen dioxide, none of the least populated cities were found to be statistically significant in terms of the change of the values of NO2. But in terms of the most populated cities, there were statistically significant decreases between 2017 and 20 and 18 and 20 in Ankara, Bursa, and Istanbul. So we can say that the NO2 levels were statistically decreased in Ankara, Bursa, and Istanbul between the pre-COVID and COVID time. For sulfur dioxide, there were no statistically significant changes in all least and highly populated cities in Turkey. For PM10, it's actually the most affected pollutant by the COVID-19 pandemic restrictions. So we can see that almost populated cities in Turkey, there was a decrease, significant decrease between the previous years. In the least populated cities, only in Bayburt, there was a decrease significantly. For PM 2.5, only there were the PM 2.5 stations were only in Ankara and Istanbul, and there were not any significant significancy in these two cities with the data. In terms of ozone, interestingly, it's increased in the least populated cities in Ardahan and Bayburt. That was a statistically significant increase, but in Istanbul, we can observe an increase in the box plot, but that was not a significance. That was not with a significance. In conclusion, in this study, we compared the values of air pollutants pre-COVID and COVID restriction times, and we found that the least populated cities were not so affected by the COVID pandemic restrictions, but in the most populated cities, there was a decrease in NO2 and PM10 concentrations. There was increase in carbon monoxide levels in Bursa and Izmir during the pandemic. There was an ozone level increase in Ardahan and Bayburt. And as a future study, maybe one study could apply a comparison between pre-pandemic, during the pandemic, and post-pandemic situations. Some recommendations, maybe renewable energy deployment could be increased and diversified. Nuclear power can help to reduce the amount of PM10 and NO2. And also transportation sector produce NO2 levels, NO2 into the atmosphere. This could be reduced by micro-mobility with bicycles and e-scooters. And also socially, maybe remote working would be encouraged, at least for applicable jobs in public and private sectors. Thank you for listening. If you have any questions, please ask.
Dear Samet, thank you very much for your nice presentation. Is there any questions? Okay, there is no questions. There are a lot of COVID-19 air quality relationship between changing in Turkey. For example, I know in our department, a lot of studies there were. So no problem. More studies means more we can understand the problem. We can choose different options. Now, thank you, Samet, and now we continue new studies. An investigation of the effects of dust transport and dust storms on PM10 and PM2.5 at airport in the Marmara region of Turkey. It is prepared by Enes Birinci, Emrah Tuncay Özdemir, Ali Deniz. I think Enes Birinci will present. Enes Birinci, you are ready?
Hello everyone. I am Enes. I am going to work as research assistant Department of Meteorological Engineering at ITU. Today I am here to talk about an investigation of the effects of dust transport and dust storms on PM10 and PM2.5 at airports in the Marmara region of Turkey. And firstly, I will give you some basic information about my content. First one is introduction, and then data and study area. Third one is material and methods. We work method and space analysis and synoptic condition, BC dream model and HY split model. And fourth one is results and discussion, and last one is conclusion. Let's start with the introduction. Particulate matter is a small air particles and suspended in the atmosphere containing liquid and solid particles, and their diameters vary between 0.001 and 100 micrometers. So they have very important effects on the world system. And previous studies, two studies, in the studies, one of them, in the studies of predicting and observing dust transport in Turkey, the blown sand BLSA event that occurred 18 April 2012 at Istanbul Sabiha and Samandıra ports was analyzed using satellite images. Deniz et al. 2013. Also, other studies, backward trajectory analysis was attempted by applying the HY split model, Sirdas et al. 2017 and Özdemir 2019. Our study the effects of the dust storm that occurred on February 2nd, 2015, on PM10 and PM2.5 were examined. Those airports are respectively Istanbul Sabiha International Airport, the International Civil Aviation Organization IC Airport, LTFJ, and Kocaeli Airport, LTFD, Çanakkale International Airport, LTBH, and Yenişehir Airport, LTVR. And data and study area, we can see that our study area, 12 airports, figure 1, but we examined 4 airports in blue. Are İstanbul Sabiha, Bursa Yenişehir, Balıkesir, and Çanakkale, because other stations are not available PM10 and PM2.5 data. Also, other stations and dust storms were not observed in metal reports. Data parameters such as wind speed, wind direction, and temperature are recorded each airport, and we download from this data from the website Mesonet and right side, and PM10 and PM2 data were downloaded Ministry of Urbanization and Climate Change, and left side. Those data are publicly available from the 2 websites. Material and methods. First one is metal and space analysis. Table 1 shows this explanation of metal and space course. What is important for us? BLDU, blowing dust, and BLSA, blowing sand, DS dust storm, DU dust, and last one is G just. And then here 2 airports, metal and space data, Istanbul Sabiha and Kocaeli Airport. First one is Istanbul Sabiha, weather phenomena, BLDU all day, blowing dust, and visibility decreased 3,200 meters at 15:20 p.m. and mean wind 19 knots, but highest value is dust 40 knots. Other station, Kocaeli Airport, between 8:50 and 10:50 dust storm, and this time it is changed, blowing dust, and reached visibility decreased 3,000 meters and 11:50. The other 2 stations, Çanakkale and Yenişehir, weather phenomena is same to airports, blowing sand, visibility at Çanakkale decreased 3,000 meters at 10:50 p.m. Highest value mean width, highest value dust, so wind 44 knots, and Yenişehir Airport visibility is the same all day, 7,000 meters, but dust reached 44 knots. And moreover, we examined cyanotic condition, DSC Dream model, HY split model. In this section, we examined the surface pressure chart and 10-meter wind map. DSC Dream model, we worked 72 backward trajectory analysis, so where we used to sort the spatial and temporal variation over the our analysis period. And by split model, we also work. And synoptic condition I skip that because I will show you figures 3, 4, 5, and 6, and here the 10-meter midpoint and surface pressure chart 31, January 2015, 00 and 12 UTC, and other slides 1st February 2015, 00 and 12 UTC. And the main reason the dust storm over the North Sahara Desert Red Square area can be briefly described as the formation of cyclone. A low pressure system and still horizontal temperature gradients rising dust flows from the Sahara Desert, and we can see that clearly. We can see southwesterly winds, and then those effects the system move the western part of Turkey, namely in the Marmara region. And we see the model, figure 7a, 30 January 2015, the concentration, the dust particles varies between 20-40 over Turkey, but figure 7c, the dust concentration increased significantly in the western part of Turkey, namely in the Marmara region, varies between 160 320 microgram per cubic meter. And also, we worked 72 backward trajectory analysis and 4 airports, Çanakkale, Kocaeli, Yenişehir, and Sabiha. We can 1,500 meter air particles and 10 meter air particles. We can follow this blue line and red line. The dust particles come from the North Sahara Desert. Similarly, Çanakkale and Kocaeli, the dust particles come from the North Sahara Desert. And when we follow this red and blue line. And also, PM10 analysis, we can see that Körfez PM10 and Lapsiki PM2.5 and Başakşehir PM10. Those stations are roughly between 30 and 40 kilometers far away airports. The Körfez PM10 reached highest value 864.5 microgram per cubic meter and 2nd February, and Lapsiki PM2.5 reached highest value 327.6 and Başakşehir Körfez PM10 52.2 microgram per cubic meter. And conclusion, this study investigation of the effects of dust transport and dust storms on PM10 and PM2.5 at the airports in the Marmara region of Turkey. The main findings as summarized as follows. The atmospheric values obtained from the air quality measurement station, Başakşehir 864.5, Lapsiki 327.6, and Körfez 552 microgram per cubic meter on power level. This is important. The cyclone that occurred North Africa level of 987 hectopascal in the central Mediterranean. The dust particles carried into the atmosphere and then came to the Marmara region of Turkey with the cyclone and southwesterly winds. And over the Turkey, as the cyclone lost its effect, the dust particles from the North Africa settled down over the Marmara region surface with the high pressure. And according to high-speed trajectory analysis, dust particles appear to have come to Turkey from the Sahara Desert for air force. Therefore, the Sahara Desert is a very important dust source for Turkey. And then, last one, BLSA, BLDU, and DU incidents were seen at 4 stations over Turkey, which slowed down the flow air traffic. And thank you for listening.
Thank you very much, Enes. Is there any questions? The subject is very interesting. You present well. Okay, end of this conference. Thank you very much for your kind contributions. Hoping to welcome you 2 years later at ATMOS 2024.
Sure.